Perhaps no equation in human history has captured the collective imagination quite like those 5 simple characters. E equals mc squared. It adorns coffee mugs and classroom walls, appears on t-shirts worn by people who might struggle to explain what it actually means, and has become shorthand for genius itself. This elegant formula, born from the mind of a patent clerk in Switzerland, fundamentally altered how we understand reality, time, space, and our place in the cosmos. Tonight, we're going to journey through the complete story of Einstein's theory of relativity, both special and general, exploring not just what these theories tell us about the universe, but how they came to be, why they matter, and how they continue to shape our understanding of existence itself. From the puzzling behaviour of light that first troubled physicists in the 19th century to the detection of gravitational waves over a century later, we'll trace the full arc of perhaps the greatest intellectual achievement in human history. Before Einstein, the universe seemed like a vast clockwork mechanism, predictable and absolute. Space was an unchanging stage upon which the drama of existence played out. Time ticked away uniformly for everyone, everywhere, marking the steady progression from past to future. Mass was mass, energy was energy, and gravity was simply a force that pulled objects together across the void. These concepts felt intuitive because they matched our everyday experience. A second lasted a second whether you were standing still or racing along in a train. A meter measured the same distance in New York as it did in Tokyo. The universe made sense in a comfortable, common-sense sort of way. But comfort and truth don't always align. As physicists probed deeper into nature's workings, troubling inconsistencies began to emerge. Light behaved in ways that defied explanation. Mercury's orbit around the Sun showed tiny deviations that Newton's laws couldn't account for. The more precisely scientists measured, the more the classical picture of reality seemed to fray at the edges. It would take a young man with an unusual gift for thought experiments, a willingness to question the most basic assumptions about reality, and the mathematical tools to transform intuition into rigorous theory to resolve these mysteries. What emerged from Einstein's work wasn't just a correction to previous theories or a minor adjustment to our understanding. It was a complete reimagining of the fundamental nature of space, time, matter, and energy. The universe revealed by relativity is far stranger than our ancestors could have imagined. Time flows at different rates depending on how fast you're moving or how strong the gravitational field around you is. Space itself can be warped and curved by the presence of mass and energy. Matter and energy are different faces of the same underlying reality, interchangeable according to that famous equation. And perhaps most unsettling of all, there is no universal now that exists across the cosmos. Simultaneity itself is relative. These ideas challenge our most basic intuitions about reality, yet they've been confirmed by countless experiments and observations. GPS satellites must account for relativistic effects to maintain accuracy. Particle accelerators routinely demonstrate the equivalence of mass and energy. Astronomers observe gravitational lensing as light bends around massive objects. Black holes, once considered mathematical curiosities too strange to exist in nature, have been photographed and studied. Gravitational waves, ripples in the fabric of space-time itself, have been detected from colliding black holes billions of light years away. The story of relativity is also deeply human. It's about a young Einstein struggling to find academic employment, working in the Swiss patent office while pondering the deepest questions about the nature of reality. It's about the collaboration and competition within the scientific community, the resistance to ideas that seem to violate common sense, and the gradual acceptance as experimental evidence mounted. It's about how one person's insight can fundamentally alter humanity's understanding of its place in the cosmos. Einstein himself was a complex figure, brilliant but also deeply human. He made mistakes, pursued dead ends for years, and sometimes resisted the implications of his own theories. He spent the last decades of his life searching unsuccessfully for a unified field theory that would combine all the forces of nature into a single framework. He famously rejected quantum mechanics' probabilistic nature, insisting that God does not play dice with the universe, even as younger physicists embraced the quantum revolution that his own work on the photoelectric effect had helped launch. The impact of relativity extends far beyond physics. It has influenced philosophy, art, literature, and popular culture. The idea that time and space are relative rather than absolute has seeped into our collective consciousness, shaping how we think about everything from science fiction scenarios to philosophical questions about the nature of reality. Writers and filmmakers have explored the implications of time dilation, creating stories about astronauts who age slower than their earthbound loved ones. Artists have tried to capture the curved geometry of space-time in visual form. Philosophers have grappled with what relativity means for concepts of causality, determinism, and free will. Yet for all its cultural impact and scientific importance, relativity remains poorly understood by most people. The mathematics can be daunting, involving tensor calculus and differential geometry that are far beyond what most of us encounter in everyday life. The concepts challenge our intuition in fundamental ways. How can time slow down? How can space be curved? What does it mean to say that mass and energy are equivalent? These questions don't have easy answers that map neatly onto our everyday experience. That's what makes the story of relativity so fascinating and important to tell in full. It's not just about equations and experiments, though we'll explore those too. It's about how human beings, using nothing but observation, logic, and mathematics, can discover truths about the universe that contradict everything our senses tell us. It's about the power of human imagination to conceive of realities beyond direct experience. And it's about how science progresses, not through sudden revelations from isolated geniuses, but through the cumulative efforts of many people building on each other's work, testing ideas against nature, and gradually assembling a more complete picture of reality. Tonight's journey will take us from the comfortable certainties of 19th century physics through the revolutionary insights of the early 20th century to the cutting-edge applications and ongoing mysteries of today. We'll explore how Einstein's theories emerged from earlier work by scientists like Maxwell, Lorentz, and Poincaré. We'll see how special relativity solved the paradoxes of electromagnetic theory while creating new puzzles about gravity. We'll follow Einstein's 8-year struggle to generalize his theory, culminating in the field equations of general relativity. We'll examine the experimental confirmations from the bending of starlight during eclipses to the recent detection of gravitational waves. And we'll consider what relativity tells us about the ultimate fate of the universe and our place within it. This is a story about light and gravity, space and time, matter and energy. But more than that, it's a story about human curiosity and the quest to understand the cosmos we inhabit. It's about how careful observation, rigorous mathematics, and bold imagination can reveal truths that transform our understanding of everything. So settle in, get comfortable, and let's begin our journey through one of the greatest intellectual adventures in human history. To truly appreciate the revolutionary nature of Einstein's theories, we need to understand the scientific worldview they replaced. By the end of the 19th century, physics had achieved remarkable successes. Newton's laws of motion and universal gravitation could predict the movements of planets with extraordinary precision, Maxwell's equations had unified electricity and magnetism into a single elegant framework. Thermodynamics had revealed the laws governing heat and energy. The atomic theory of matter was gaining acceptance, and the periodic table had brought order to chemistry. Many physicists believed that the fundamental laws of nature had been discovered, and all that remained was to work out the details and improve the precision of measurements. This classical worldview rested on several fundamental assumptions that seemed so obvious they were rarely questioned. Space was assumed to be absolute and unchanging, like an infinite three-dimensional grid extending in all directions. This space provided the fixed stage upon which all physical events occurred. You could, in principle, set up a coordinate system and specify the exact location of any object in the universe. Distance was distance, the same for everyone regardless of their motion or position. Time, too, was absolute in the classical picture. It flowed uniformly throughout the universe, like a cosmic clock ticking away the seconds for everyone simultaneously. If an event occurred on Earth at noon, it was noon throughout the universe, at that instant. The concept of simultaneity was unproblematic. Events either happened at the same time or they didn't, and this was an objective fact independent of any observer. Past, present, and future were sharply defined and the same for everyone. Matter was understood to be made of particles, tiny billiard balls that interacted through forces. These particles had definite positions and velocities at each moment in time. If you knew the position and velocity of every particle in the universe at one instant, along with all the forces acting between them, you could in principle calculate the entire future and past of the universe. This was the clockwork universe of Laplace's demon, completely deterministic and predictable. Energy came in various forms, such as kinetic energy of motion, potential energy of position, heat energy, and electromagnetic energy, but these were seen as distinct phenomena. The conservation of energy was a fundamental principle, stating that energy could neither be created nor destroyed, only transformed from one form to another. Similarly, mass was conserved in all interactions. You might rearrange atoms in chemical reactions, but the total mass before and after remained the same. Gravity, according to Newton, was a force that acted instantaneously across space. Every mass in the universe pulled on every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This force somehow reached across empty space instantly, no matter how far apart the objects were. Newton himself was uncomfortable with this action at a distance, but the theory worked so well in practice that most physicists accepted it. Light was understood to be a wave, specifically an electromagnetic wave, as described by Maxwell's equations. These waves consisted of oscillating electric and magnetic fields that propagated through space at a fixed speed, approximately 300,000 kilometers per second. But waves, physicists reasoned, needed a medium to propagate through. Sound waves travel through air, water waves through water, so light waves must travel through something. This hypothetical medium was called the luminiferous ether, an invisible, intangible substance that filled all of space. The ether was a peculiar concept. It had to be incredibly rigid to support the high-speed propagation of light waves, yet it couldn't impede the motion of planets and other objects moving through it. It had to fill all of space, even the vacuum between stars, yet be completely undetectable, except for its role in carrying light. Despite these conceptual difficulties, most physicists accepted the ether as necessary for understanding light propagation. This classical framework had been remarkably successful. It could explain the motion of projectiles, the orbits of planets, the behavior of gases, the flow of heat, and countless other phenomena. Engineers used classical physics to design bridges, steam engines, and electrical devices. Astronomers used it to predict eclipses and discover new planets. The agreement between theory and observation was often spectacular, accurate to many decimal places. But cracks were beginning to show in this edifice. Some were minor puzzles that might eventually be resolved within the classical framework. Others were more fundamental challenges that suggested something was deeply wrong with the basic assumptions. The most troubling issues centered around light and electromagnetism. Maxwell's equations, formulated in the 1860s, had been a triumph of theoretical physics. They showed that electricity and magnetism were two aspects of a single phenomenon, electromagnetism. They predicted the existence of electromagnetic waves that travelled at the speed of light, leading to the realization that light itself was an electromagnetic wave. This unification was beautiful and powerful, but it raised disturbing questions. According to Maxwell's equations, electromagnetic waves always travelled at the same speed in vacuum, approximately 300,000 kilometers per second. But speed relative to what? In classical physics, speed was always measured relative to something. A train might be moving at 60 kilometers per hour relative to the ground, but relative to a passenger walking forward in the train, it would be moving at 59 kilometers per hour. There was no such thing as absolute speed, only relative speed. If light was a wave in the ether, then its speed should be relative to the ether. But this led to a puzzling consequence. The Earth moves through space in its orbit around the Sun at about 30 kilometers per second. If the ether was stationary, then we should be moving through it, creating an ether wind. Light travelling in the direction of Earth's motion should appear to move faster than light travelling perpendicular to it, just as sound appears to travel faster downwind than upwind. In 1887, Albert Michelson and Edward Morley performed a famous experiment to detect this ether wind. They used an interferometer, a device that could detect incredibly small differences in the speed of light in different directions. The experiment was sensitive enough to easily detect the expected effect if it existed. But no matter how they oriented their apparatus or what time of year they performed the measurement, they found no difference in the speed of light in different directions. Light seemed to travel at the same speed regardless of the Earth's motion through the supposed ether. This null result was deeply troubling. Various explanations were proposed. Maybe the Earth dragged the ether along with it, like a ship dragging water, but this contradicted other observations, such as stellar aberration, which showed that the Earth's motion did affect the apparent position of stars. Maybe the ether was partially dragged by the Earth. But these theories became increasingly complex and unsatisfactory. George Fitzgerald and Hendrik Lorentz independently proposed a radical solution. Maybe objects contracted in the direction of motion through the ether by just the right amount to make the ether wind undetectable. This length contraction would affect the measuring apparatus itself, making it impossible to detect the ether wind. Lorentz worked out the mathematical details, showing that if lengths contracted by a factor that depended on velocity, and if time also dilated by a related factor, then Maxwell's equations would work the same way in all reference frames moving at constant velocity. These Lorentz transformations, as they came to be called, were mathematically correct and solved the immediate problem, but they seemed physically absurd. Why would objects shrink just because they were moving? What mechanism could cause time to slow down? Lorentz himself viewed these effects as real physical changes caused by motion through the ether, but he couldn't explain the underlying mechanism. The transformations worked mathematically, but they seemed to lack physical meaning. Another puzzle concerned the nature of light itself. Maxwell's equations described light as a wave, and many experiments confirmed its wave nature. Light showed interference patterns, diffraction, and other characteristic wave behaviors. But other experiments suggested light had particle-like properties. The photoelectric effect discovered by Heinrich Hertz in 1887 was particularly puzzling. When light struck certain metals, it ejected electrons, but the energy of the ejected electrons depended on the frequency of the light, not its intensity. A dim blue light could eject electrons with more energy than a bright red light. This made no sense if light was purely a wave. Black body radiation presented another challenge. A black body is an idealized object that absorbs all radiation that falls on it and emits radiation based only on its temperature. Classical physics predicted that a black body should emit infinite energy at high frequencies, an obviously incorrect result known as the ultraviolet catastrophe. Max Planck solved this problem in 1900 by proposing that energy was emitted in discrete packets or quanta proportional to the frequency. But this quantization of energy didn't fit well with classical physics. The orbit of Mercury provided yet another puzzle. Newton's theory of gravity predicted that planetary orbits should be ellipses, with the Sun at one focus. In reality, these ellipses slowly rotate or precess due to the gravitational influence of other planets. For Mercury, the innermost planet, astronomers could calculate the expected precession based on the gravitational pulls of all the other known planets. But Mercury's orbit precessed slightly faster than predicted, by about 43 arc-seconds per century. This was a tiny effect, but it was measurable and unexplained. Some astronomers proposed an undiscovered planet even closer to the Sun, dubbed Vulcan, but searches for this planet found nothing. Radioactivity, discovered by Henri Becquerel in 1896, presented its own mysteries. Certain elements spontaneously emitted radiation and transformed into other elements. This seemed to violate the conservation of energy, as the radiation carried energy away with no apparent source. It also violated the classical idea that elements were immutable. Marie and Pierre Curie's work on radioactive elements revealed that vast amounts of energy were somehow locked inside atoms, but classical physics couldn't explain how. These puzzles might seem unrelated, but they all pointed to limitations in the classical worldview. The behavior of light didn't fit neatly into the framework of absolute space and time. The stability of atoms and the nature of atomic spectra couldn't be explained by classical mechanics. The source of the sun's energy was a mystery, as no known chemical or gravitational process could power it for the geological timescales that evidence demanded. By the early 20th century, physics was ripe for revolution. The old certainties were crumbling and new ideas were needed, but the changes required weren't minor adjustments or corrections. They would require abandoning some of the most fundamental assumptions about the nature of space, time, matter, and energy. It would take a young patent clerk with an unusual ability to think deeply about fundamental principles to see the way forward. The stage was set for Einstein's entrance. The puzzles were known, the mathematical tools were being developed, and the scientific community was ready, if not eager, for new ideas. What came next would transform not just physics, but our entire understanding of reality. Albert Einstein was born on March 14, 1879, in Ulm, a small city in the Kingdom of Württemberg in the German Empire. His parents, Hermann and Pauline Einstein, were secular middle-class Jews. Hermann ran an electrical equipment business with varying degrees of success, and the family moved several times during Albert's childhood as business fortunes rose and fell. These early years gave little indication that young Albert would become the most celebrated scientist of the 20th century. Indeed, Einstein's early development caused his parents some concern. He was slow to speak, not uttering his first words until age 2 or 3, and even then, he would quietly repeat sentences to himself before speaking them aloud. This habit earned him the family nickname Der Deperter, roughly meaning the dopey one. Some biographers have speculated that Einstein may have had a form of autism or learning disability, though such retrospective diagnoses are necessarily speculative. What seems clear is that from an early age Einstein thought differently than those around him. Despite the later myth that Einstein was a poor student, he actually excelled in mathematics and physics from a young age. He taught himself algebra and geometry, and by age 12 he had learned differential and integral calculus on his own, years before it would be taught in school. A family friend, Max Talmud, introduced him to popular science books and philosophical works, including Kant's Critique of Pure Reason, which the young Einstein devoured eagerly. These early intellectual experiences shaped his lifelong habit of thinking deeply about fundamental questions. Einstein's relationship with authority and formal education was complicated from the start. He attended the Luitpold Gymnasium in Munich, where the rigid, militaristic style of German education clashed with his questioning nature. He despised rote learning and the authoritarian atmosphere, later describing his teachers as resembling army sergeants. This resistance to authority would remain a defining characteristic throughout his life, enabling him to question fundamental assumptions that others took for granted. A critical moment in Einstein's intellectual development came when he was around 16. He imagined what it would be like to ride alongside a beam of light. According to classical physics, he should see a stationary electromagnetic wave, frozen in space. But Maxwell's equations didn't allow for such stationary electromagnetic waves. This thought experiment troubled him for years and would eventually lead to special relativity. It showed his remarkable ability to translate abstract physical concepts into vivid mental images. When his father's business failed again in 1894, the family moved to Italy, leaving Albert behind to finish his schooling. But he despised the gymnasium so much that he obtained a doctor's note claiming nervous exhaustion and left to join his family in Italy. This meant leaving without a diploma, a decision that would complicate his educational path. To continue his studies, he would need to pass an entrance exam for the Swiss Federal Polytechnic in Zurich. Einstein failed this entrance exam on his first attempt in 1895, though he excelled in mathematics and physics. His weakness in language, botany and zoology led the examiner to suggest he complete his secondary education first. He enrolled in the cantonal school in Aarau, Switzerland, where he thrived in the more liberal and informal atmosphere. The Swiss educational system, with its emphasis on independent thought and visual understanding, suited Einstein perfectly. He lived with the family of Jost Winterler, the school's principal, and fell in love with their daughter Marie, his first romance. In Aarau, Einstein began to develop the thought experiments that would become his trademark approach to physics. He would visualize physical scenarios in his mind, working through the logical consequences of fundamental principles. This visual, intuitive approach complemented his mathematical abilities and would prove crucial in developing relativity. He also began to question the concept of the ether and absolute motion, wondering how one could ever detect uniform motion through space if there were no absolute reference frame. Einstein successfully gained admission to the Zurich Polytechnic in 1896, where he studied to become a teacher of mathematics and physics. The Polytechnic, later renamed ETH Zurich, was one of Europe's premier technical universities. There he met Mileva Maric, the only woman in his physics class, and his future wife. Their relationship was both romantic and intellectual. They studied together and discussed physics problems in their letters. Some historians have debated Mileva's role in Einstein's early work, though most conclude that while she was a sounding board and study partner, the revolutionary ideas were primarily his. Einstein's university years revealed both his brilliance and his difficulties with formal education. He often skipped classes he found boring, preferring to study on his own or with friends. He read the works of Ernst Mach, whose critique of Newtonian absolute space and time influenced his thinking. He studied Maxwell's electromagnetic theory, though it wasn't part of the official curriculum. His independent approach irritated some professors, particularly Heinrich Weber, who told Einstein, "You're a clever fellow, but you have one fault. You won't let anyone tell you anything." This antagonistic relationship with his professors would have serious consequences. When Einstein graduated in 1900, he was the only member of his graduating class not offered an assistantship. Despite his obvious brilliance in physics, his reputation as difficult and arrogant led professors to pass him over. He spent 2 frustrating years seeking academic employment, supporting himself through temporary teaching positions and tutoring. During this period, he faced genuine financial hardship and professional rejection that might have broken a less determined person. Einstein's personal life during this period was also complicated. His relationship with Mileva faced opposition from his parents, who disapproved of her Serbian Orthodox background and her older age. When Mileva became pregnant in 1901, it created a crisis. Their daughter Liesel was born in early 1902, but her fate remains one of the mysteries of Einstein's biography. She may have been given up for adoption or died in infancy from scarlet fever. Einstein and Mileva married in January 1903, after he had secured stable employment. That employment came through the intervention of Marcel Grossmann, a friend from the Polytechnic, whose father helped Einstein secure a position at the Swiss Patent Office in Bern. Einstein started as a technical expert third class in June 1902, examining patent applications for electromagnetic devices. The job, which many would consider a dead end for a physicist, proved ideal for Einstein. It provided financial stability, left him time to think about physics, and exposed him to practical applications of electromagnetic theory. The patent office years, from 1902 to 1909, were extraordinarily productive for Einstein. His job required him to quickly grasp the essence of inventions and identify their key principles, skills that transferred well to theoretical physics. The work was intellectually engaging but not exhausting, leaving him mental energy for his own research. He would later call the patent office that worldly cloister where I hatched my most beautiful ideas. Einstein formed a small discussion group with friends, jokingly called the Olympia Academy, where they read and debated works of physics, philosophy, and literature. Members included Maurice Solovin and Conrad Habicht, and they met regularly to discuss the works of Mach, Hume, Poincaré, and others. These discussions sharpened Einstein's thinking about the philosophical foundations of physics, particularly questions about the nature of space, time, and causality. During these years, Einstein published several papers on statistical mechanics and thermodynamics, developing ideas independently that were similar to those of Josiah Willard Gibbs. These papers, while not revolutionary, showed his deep understanding of statistical physics and his ability to work at the forefront of research despite his isolation from academic centres. They also revealed his interest in the atomic theory of matter, which was still controversial at the time. By 1905, Einstein had been thinking about the problems of electrodynamics and relative motion for nearly a decade. His thought experiments had convinced him that the principle of relativity, the idea that the laws of physics should be the same in all inertial reference frames, must be a fundamental principle of nature. But reconciling this with the constant speed of light seemed impossible within the framework of classical physics. The breakthrough came suddenly in May 1905 during a discussion with his friend Michel Bessot. Einstein realized that the solution required abandoning the concept of absolute simultaneity. If observers in relative motion could disagree about whether two events happened at the same time, then the paradoxes disappeared. Time itself must be relative. This insight, which seems so foreign to common sense, was the key that unlocked special relativity. What followed was an extraordinary burst of creativity. In 1905, his miracle year, Einstein published 4 groundbreaking papers that would transform physics. The first, on the photoelectric effect, proposed that light consisted of discrete quanta of energy, later called photons. This paper, which would eventually earn him the Nobel Prize, was crucial for the development of quantum mechanics. The second paper, on Brownian motion, provided convincing evidence for the existence of atoms by explaining the random motion of particles suspended in fluids. The third paper, submitted in June, introduced special relativity, though Einstein called it On the Electrodynamics of Moving Bodies. In just 30 pages, with no references to other papers, Einstein derived the Lorentz transformations from 2 simple postulates. The laws of physics are the same in all inertial frames, and the speed of light in vacuum is constant for all observers. The paper was remarkable for its clarity and simplicity, stripping away the complex ether theories and replacing them with a clean, logical structure. The fourth paper, submitted in September as an addendum to the relativity paper, contained the famous equation E equals mc squared, though not quite in that form. Einstein showed that mass and energy were equivalent, that an object's mass increased with its energy content. This brief 3-page paper would have profound implications for understanding the source of stellar energy and the possibility of nuclear weapons. These papers were submitted to Annalen der Physik, one of the leading physics journals, by an unknown patent clerk with no academic position or reputation. That they were published at all is remarkable. That they revolutionized physics is extraordinary. The editor, Max Planck, recognized their importance, though even he initially had doubts about some of Einstein's conclusions. The response from the physics community was initially muted. The papers were so original and their implications so radical that many physicists didn't know what to make of them. Some dismissed them as too speculative. Others recognized their mathematical elegance but doubted their physical reality. A few, including Planck and the mathematician Hermann Minkowski, immediately grasped their significance and began building on Einstein's work. Einstein himself seemed remarkably calm about his revolutionary achievements. He continued working at the patent office, was promoted to technical expert second class, and lived quietly with Mileva and their young son, Hans Albert, born in 1904. He submitted his relativity paper as a doctoral dissertation to the University of Zurich, but was told it was too short. He resubmitted his paper on molecular dimensions, which was accepted, finally earning him the title Dr. Einstein in 1906. The young patent clerk had solved problems that had puzzled the greatest physicists of his generation. He had shown that space and time were not absolute but relative, that mass and energy were equivalent, and that light behaved as both wave and particle. But this was just the beginning. Einstein knew that special relativity was incomplete. It applied only to uniform motion and couldn't account for gravity or acceleration. The quest to generalize relativity would consume the next decade of his life and produce an even more radical transformation of our understanding of the universe. The year 1905 stands as perhaps the most remarkable single year in the history of physics. In this one year, working alone in his spare time, Einstein produced insights that would normally be considered career-defining achievements for multiple scientists. Each of his 4 major papers from that year opened new fields or resolved long-standing puzzles. But it was the paper on special relativity that most fundamentally challenged our understanding of reality itself. Einstein's approach to special relativity was characteristically elegant and minimalist. Rather than trying to fix the complications and contradictions of ether theories, he swept them all away with two simple postulates. First, the principle of relativity. The laws of physics are the same in all inertial reference frames. Second, the constancy of the speed of light. Light travels at the same speed in vacuum for all observers, regardless of their motion or the motion of the light source. From these two principles, using only logical deduction and basic mathematics, Einstein derived results that seem to defy common sense. The paper itself, submitted to Annalen der Physik on June 30th, 1905, was titled On the Electrodynamics of Moving Bodies. The title was deliberately modest, giving no hint of the revolutionary nature of its contents. Einstein began not with grand philosophical statements, but with a simple observation about electromagnetic induction. When a magnet moves relative to a conductor, an electric current is induced. Classical physics gave different explanations depending on whether you considered the magnet or the conductor to be moving, even though the observable phenomenon was the same. This asymmetry troubled Einstein, suggesting something was wrong with the classical framework. Einstein's writing style in this paper was unlike typical scientific papers of the era. There were no citations, no references to the work of Lorentz, Poincaré, or other physicists who had grappled with these problems. This wasn't arrogance, but rather reflected Einstein's independent approach. He had worked out these ideas largely on his own, through pure thought, and he presented them as a logical structure built from first principles. The paper reads almost like a mathematical proof, each conclusion following inevitably from what came before. The first revolutionary consequence emerged quickly: the relativity of simultaneity. Einstein showed through a simple thought experiment that two events that appear simultaneous to one observer might not appear simultaneous to another observer in relative motion. Imagine a train moving at high speed past a platform. Lightning strikes both ends of the train simultaneously, as judged by an observer on the platform. Light from both strikes reaches the platform observer at the same time, confirming simultaneity. But an observer in the middle of the train is moving toward one lightning flash and away from the other. They see the forward strike first, then the rear strike. For this observer, the strikes were not simultaneous. This wasn't just an optical illusion or a delay in signal transmission. Einstein showed that there was no absolute fact of the matter about whether the strikes were really simultaneous. Simultaneity itself was relative, depending on the observer's state of motion. This shattered the classical notion of absolute time, the idea that there was a universal now extending throughout the universe. Different observers moving at different velocities would slice up space-time into now moments differently. From this foundation, Einstein derived the phenomena of time dilation and length contraction that Lorentz had discovered mathematically. But while Lorentz saw these as real physical effects caused by motion through the ether, Einstein showed they were necessary consequences of the geometry of space-time itself. A moving clock runs slow not because motion somehow mechanically affects the clock's mechanism, but because time itself passes differently for observers in relative motion. The time dilation formula emerged naturally from Einstein's analysis. If two observers are moving relative to each other at velocity v and the speed of light is c, then time intervals are related by the factor gamma equals 1 over the square root of 1 minus v squared over c squared. This Lorentz factor, as it came to be known, appears throughout special relativity. When v is much smaller than c, as in everyday experience, gamma is essentially 1 and relativistic effects are negligible. But as v approaches c, gamma approaches infinity and relativistic effects become dramatic. Einstein illustrated these effects with vivid thought experiments. Consider two identical twins. One stays on Earth while the other travels to a distant star at high speed. Due to time dilation, the travelling twin ages more slowly. Upon reunion, the travelling twin is younger than the stay-at-home twin. This twin paradox, as it came to be known, seems paradoxical because relativity suggests that each twin could consider themselves at rest and the other in motion. The resolution lies in the fact that the travelling twin must accelerate to turn around, breaking the symmetry. The twin who accelerates is the one who ages less. Length contraction followed by the same logic. Objects moving relative to an observer appear shortened in the direction of motion by the same Lorentz factor. A meter stick moving at 87% of light speed would appear only half a meter long. Again, this isn't a mechanical compression but a consequence of how space and time are related. Different observers disagree about which events are simultaneous, and this disagreement manifests as disagreement about lengths. Einstein then turned to the transformation of velocities. In classical physics, velocities simply add. If you're on a train moving at 50 kilometers per hour and walk forward at 5 kilometers per hour, your velocity relative to the ground is 55 kilometers per hour. But Einstein showed this simple addition breaks down at high speeds. The relativistic velocity addition formula ensures that no matter how you combine velocities below the speed of light, the result never exceeds the speed of light. If a spaceship travelling at 90% of light speed fires a projectile forward at 90% of light speed relative to itself, the projectile's speed relative to a stationary observer isn't 180% of light speed, but about 99.4% of light speed. This preservation of the light speed limit revealed something profound about the structure of space-time. The speed of light wasn't just the speed at which light happened to travel, it was a fundamental feature of the geometry of space and time. It represented the maximum rate at which cause and effect could propagate through the universe, the ultimate speed limit built into the fabric of reality itself. The implications for our understanding of energy and momentum were equally revolutionary. Einstein showed that the classical formulas for kinetic energy and momentum were only approximations valid at low speeds. The relativistic momentum of an object wasn't simply mass times velocity, but mass times velocity divided by the square root of 1 minus velocity squared over c squared. As an object's velocity approached the speed of light, its momentum approached infinity, explaining why no massive object could ever reach light speed. It would require infinite energy to accelerate any mass to the speed of light. This led to one of the most profound insights of special relativity. In a short follow-up paper submitted in September 1905, Einstein explored the relationship between mass and energy. He considered a body emitting light in opposite directions and analysed the process from different reference frames. Through careful calculation, he showed that when a body emits energy E in the form of radiation, its mass decreases by E divided by c squared. Rearranging this relationship gave the famous equation, though Einstein originally wrote it as m equals E over c squared rather than E equals mc squared. This equivalence of mass and energy was perhaps the most shocking result of special relativity. It suggested that mass wasn't the immutable quantity classical physics assumed but could be converted into energy and vice versa. Every object with mass contained enormous amounts of energy, locked within its very substance. A single gram of matter, if completely converted to energy, would release about 90 trillion joules, equivalent to the explosion of 21,000 tons of TNT. This wasn't just a theoretical curiosity. It would later explain the source of stellar energy and enable both nuclear power and nuclear weapons. Einstein's derivation of mass-energy equivalence was remarkably simple, occupying just 3 pages. Yet it overturned centuries of belief in the separate conservation of mass and energy. Instead, it was mass energy that was conserved, a unified quantity that could transform between its different manifestations. When you heat an object, its mass actually increases slightly due to the added thermal energy. When an atom emits light, it becomes slightly lighter. These effects are tiny at everyday energies, but they become dramatic in nuclear reactions, where significant fractions of mass convert to energy. The paper also resolved a puzzle about electromagnetic radiation. Classical physics knew that light carried energy and momentum, but the relationship between them seemed arbitrary. Special relativity showed that for light, energy equals momentum times c, a relationship that followed necessarily from the structure of spacetime. Light, having no mass, always travels at speed c and carries momentum equal to its energy divided by c. As word of Einstein's papers spread through the physics community, reactions varied widely. Some immediately recognized their importance. Max Planck, already famous for his work on quantum theory, became an early champion of relativity. He organized the first seminars on the subject and encouraged his students to develop Einstein's ideas further. Hermann Minkowski, who had been one of Einstein's professors at the Zurich Polytechnic, reformulated special relativity in terms of 4-dimensional spacetime, providing the mathematical framework that would prove essential for general relativity. Others were more skeptical. Many physicists found it hard to abandon the intuitive notions of absolute space and time. The idea that simultaneity was relative seemed to undermine causality itself. How could the universe function if there was no universal now? Some attempted to preserve the ether by proposing that Einstein's theory was merely a mathematical convenience, that the Lorentz transformations described real physical effects in an absolute ether frame that just happened to be undetectable. Henri Poincaré, the great French mathematician and physicist, had come tantalizingly close to discovering special relativity himself. He had recognized the principle of relativity and understood much of the mathematics, but he never made Einstein's conceptual leap of abandoning absolute time. Even after Einstein's papers, Poincaré continued to speak of the ether and seemed never to fully accept the radical implications of relativity. This illustrates how even brilliant minds can be constrained by conceptual frameworks. The experimental evidence for special relativity accumulated gradually. The Michelson-Morley experiment, though performed before Einstein's theory, was retroactively seen as confirmation. More direct tests came from studying fast-moving particles. Electrons accelerated to high speeds. In cathode ray tubes showed the mass increase predicted by relativity. Radioactive decay products, naturally occurring particles moving at significant fractions of light speed, exhibited time dilation and momentum changes exactly as Einstein predicted. One of the most elegant confirmations came from cosmic ray muons. These particles are created when cosmic rays strike the upper atmosphere, about 10 kilometers above Earth's surface. Muons are unstable, with a half-life of about 2 microseconds when at rest. Even travelling at near light speed, they shouldn't survive long enough to reach the ground in the numbers observed. But time dilation allows them to survive the journey. From the muon's perspective, length contraction shortens the distance to the ground. Either way you calculate it, relativity explains their survival. The practical applications of special relativity emerged slowly at first. For most engineering purposes, classical physics remained perfectly adequate. Objects in everyday experience move at speeds so much slower than light that relativistic effects are negligible. But as technology advanced, situations arose where relativity couldn't be ignored. Particle accelerators had to account for relativistic mass increase when calculating the magnetic fields needed to bend particle beams. Television tubes and electron microscopes required relativistic corrections for precise focusing of high-speed electron beams. The global positioning system provides perhaps the most familiar modern application. GPS satellites orbit Earth at about 14,000 kilometers per hour, fast enough that special relativistic time dilation causes their clocks to run about 7 microseconds per day, slower than Earth clocks. Without correcting for this effect, GPS positions would drift by about 2 kilometers per day. The system's remarkable accuracy, pinpointing locations to within meters, depends on properly accounting for relativistic effects. Special relativity also transformed our understanding of electromagnetism. What appears as an electric field to one observer might appear as a combination of electric and magnetic fields to another observer in relative motion. This isn't just a change in perspective. Electric and magnetic fields are genuinely different aspects of a unified electromagnetic field, their apparent separation depending on the observer's reference frame. This unification, implicit in Maxwell's equations, became clear only through Einstein's relativistic framework. The philosophical implications of special relativity extended far beyond physics. The theory challenged fundamental assumptions about the nature of reality, suggesting that properties we thought were absolute were actually relative to the observer. This relativity of simultaneity implied that past, present, and future might not be as distinct as we intuitively believe. Events that one observer sees as happening now might be in another observer's past or future. This led some philosophers and physicists to embrace a block universe view, where all events across time exist eternally in four-dimensional space-time. Yet special relativity also revealed new absolutes. While space and time separately were relative, the space-time interval between events was absolute. The same for all observers. The speed of light was absolute. The laws of physics themselves were absolute, taking the same form in all inertial frames. In overthrowing some absolutes, Einstein discovered deeper ones, suggesting that reality had an objective structure, even if different observers perceived it differently. By 1907, Einstein himself had moved beyond special relativity. He realized that the theory was incomplete because it applied only to observers moving at constant velocity. It couldn't handle acceleration or gravity. In what he later called the happiest thought of my life, Einstein realized that a person falling freely doesn't feel their own weight. This equivalence between acceleration and gravity would become the foundation of general relativity. But developing this insight into a complete theory would require 8 more years of intense intellectual effort, new mathematical tools, and an even more radical reimagining of space and time. The impact of special relativity continued to ripple through physics. It provided the framework for understanding high-energy particle physics, where particles routinely travel at speeds approaching light. It revealed the deep connection between space and time, matter and energy, electricity and magnetism. It showed that the universe was far stranger than classical physics imagined, yet also more unified, with seemingly disparate phenomena arising from common underlying principles. To truly grasp special relativity, we need to move beyond the historical development and delve deeply into what the theory actually tells us about the nature of reality. The concepts are counterintuitive, contradicting our everyday experience, but they follow logically from Einstein's 2 postulates. Understanding these ideas requires us to abandon preconceptions and think carefully about what we mean by fundamental concepts, like time, space, and motion. Let's begin with the notion of a reference frame. A reference frame is essentially a perspective from which to observe and measure events in the universe. It consists of a coordinate system for specifying positions and a set of synchronized clocks for measuring time. An inertial reference frame is one that isn't accelerating. Objects within it obey Newton's first law, remaining at rest or in uniform motion unless acted upon by a force. Special relativity deals exclusively with inertial frames, leaving accelerated frames for general relativity. The principle of relativity states that all inertial reference frames are equivalent for describing physical laws. There's no experiment you can perform within an inertial frame to determine whether you're really moving or at rest. This might seem obvious, but it has profound implications. If you're in a smoothly travelling train with the windows covered, no mechanical experiment can tell you whether the train is moving or stationary. The laws of physics work exactly the same way, regardless. This principle was actually known before Einstein. Galileo understood that motion was relative, that there was no absolute standard of rest. What Einstein added was the recognition that this principle applied to all of physics, including electromagnetism, and that maintaining this principle required abandoning absolute time. The constancy of light speed for all observers was incompatible with absolute time, and Einstein chose to preserve the principle of relativity. To understand how time becomes relative, consider a simple thought experiment involving a light clock. Imagine a device consisting of two mirrors separated by a fixed distance, with a pulse of light bouncing between them. Each round trip of the light pulse marks one tick of the clock. If the clock is at rest relative to you, the light travels straight up and down, covering a distance of twice the mirror separation per tick. Now imagine the same clock moving horizontally relative to you at high speed. From your perspective, the light pulse must travel a diagonal path to keep up with the moving mirrors. This diagonal path is longer than the vertical path, but the speed of light remains constant. Therefore, from your perspective, the moving clock takes longer to complete each tick. The moving clock runs slow. This isn't an illusion or a mechanical effect. Time itself passes more slowly for the moving clock. The amount of time dilation depends on the relative velocity. For speeds much less than light speed, the effect is negligible. A clock moving at 1% of light speed runs only about 0.005% slower. But as speeds approach light speed, the effect becomes dramatic. At 90% of light speed, time passes at less than half the normal rate. At 99.9% of light speed, time slows by a factor of about 22. As velocity approaches light speed, time dilation approaches infinity. This leads to fascinating possibilities. A journey to a star 4 light-years away, travelling at 99.9% of light speed, would take just over 4 years as measured by Earth observers. But for the travellers, only about 2 months would pass. At even higher speeds, the effect becomes more extreme. A round trip to the Andromeda Galaxy, 2.5 million light-years away, could be completed within a human lifetime for the travellers, though millions of years would pass on Earth. Length contraction is intimately connected to time dilation. Just as time intervals appear different to observers in relative motion, so do spatial distances. An object moving relative to you appears contracted in the direction of motion by the same Lorentz factor that governs time dilation. A spaceship 100 meters long, travelling at 90% of light speed, would appear only 44 meters long to a stationary observer. It's crucial to understand that these effects are symmetric. If you see my clock running slow, I see your clock running slow. If you see my meter stick contracted, I see your meter stick contracted. This might seem paradoxical, but it's a necessary consequence of the relativity principle. There's no absolute standard to determine who is really moving, so the effects must be reciprocal. Each observer's measurements are correct within their own reference frame. The resolution of apparent paradoxes often lies in careful consideration of simultaneity. Events that are simultaneous in one frame aren't simultaneous in another. This relativity of simultaneity is perhaps the most difficult aspect of special relativity to internalize. We're accustomed to thinking of now as a universal concept extending throughout space, but relativity shows this is an illusion created by the slow speeds of everyday life. Consider two events separated in space, but simultaneous in your reference frame. An observer moving relative to you will disagree about their simultaneity. Depending on their direction of motion, they might see either event happen first. This isn't due to signal delays or observation limitations. It's a fundamental feature of space-time geometry. Different observers slice four-dimensional space-time into three-dimensional now moments differently. This has profound implications for causality. Events that have a time-like separation, meaning a signal travelling at or below light speed, could connect them, maintain their causal order in all reference frames. If event A causes event B in one frame, this causal relationship holds in all frames. But events with space-like separation, too far apart for light to travel between them in the available time, have no absolute time ordering. Different observers disagree about which happened first, and neither is wrong. The speed of light emerges as the fundamental constant that structures space-time. It's not just the speed at which light happens to travel, but the maximum speed of causality itself. Information, matter, energy, and any causal influence cannot travel faster than light. This isn't a technological limitation, but a feature of space-time geometry. Faster than light travel would allow effect to precede cause in some reference frames, creating logical paradoxes. To better understand these relationships, Hermann Minkowski introduced the concept of space-time in 1908. Instead of treating space and time separately, Minkowski united them into a four-dimensional continuum. Events are points in space-time, specified by three spatial coordinates and one time coordinate. The history of an object traces out a world line through space-time. In this space-time picture, the effects of special relativity become geometrical. Different observers use different coordinate systems to describe the same space-time. What one observer sees as purely spatial separation, another sees as a mix of spatial and temporal separation. The Lorentz transformations are analogous to rotations, but instead of rotating in space, they're rotations between space and time dimensions. The invariant quantity in space-time is the space-time interval between events. For two events separated by distances delta x, delta y, delta z in space, and delta t in time, the space-time interval squared is c squared, times delta t squared minus delta x squared minus delta y squared minus delta z squared. This quantity has the same value for all observers, even though they disagree about the individual space and time separations. This space-time interval divides pairs of events into three categories. If the interval is positive, the events have time-like separation and can be causally connected. If it's zero, they have light-like separation and could be connected by a light signal. If it's negative, they have space-like separation and cannot causally influence each other. These categories are absolute, agreed upon by all observers. The energy-momentum relationship in special relativity reveals deep connections between quantities that seemed unrelated in classical physics. The total energy of an object equals gamma times mc squared, where m is the rest mass and gamma is the Lorentz factor, depending on velocity. This total energy includes both the rest energy, mc squared, and the kinetic energy. At low speeds, this reduces to the classical formula for kinetic energy plus the rest energy. Momentum in relativity is gamma times mv, which approaches the classical mv at low speeds, but increases without limit as velocity approaches light speed. Energy and momentum are related by E squared equals P squared, C squared plus M squared C to the fourth, where P is momentum. For massless particles like photons, This reduces to E equals pc, explaining why light carries momentum despite having no mass. These relationships reveal that mass, energy, and momentum are different aspects of a unified, four-dimensional energy-momentum vector in spacetime. Just as space and time are unified in spacetime, energy and momentum are unified in this four-vector. Different observers measure different values for energy and momentum, but the magnitude of the four-vector related to the rest mass is invariant. The addition of velocities in special relativity follows a non-intuitive formula that ensures no combination of sublight speeds yields a superlight speed. If object A moves at velocity u relative to u, and object B moves at velocity v relative to A in the same direction, then B's velocity relative to u isn't u plus v, but rather u plus v divided by 1 plus uv over c squared. For small velocities, this approximately equals u plus v, recovering the classical result. But as velocities approach light speed, the sum always remains below c. This velocity addition formula has interesting consequences. No matter how many successive boosts you apply, you never reach light speed. You can get arbitrarily close, but never reach it. From the perspective of a particle being accelerated, each boost provides the same change in velocity, but from an external perspective, the increments get smaller as the particle approaches light speed. Special relativity also modifies our understanding of forces and acceleration. A constant force doesn't produce constant acceleration, as in classical mechanics. As an object's velocity increases, the same force produces less acceleration. The relationship between force and acceleration becomes F equals gamma cubed ma for force parallel to velocity, and F equals gamma mma for force perpendicular to velocity. This explains why particle accelerators require ever-increasing amounts of energy to achieve small increases in speed as particles approach light speed. The electromagnetic field transforms in interesting ways between reference frames. What appears as a purely electric field in one frame appears as a combination of electric and magnetic fields in another. A charged particle at rest produces only an electric field, but the same particle viewed from a moving frame produces both electric and magnetic fields. This reveals that electricity and magnetism aren't separate phenomena, but different aspects of the unified electromagnetic field. This transformation of fields explains many electromagnetic phenomena. The magnetic force on a moving charged particle can be understood as an electric force in the particle's rest frame. The magnetic field around a current-carrying wire arises from length contraction of the moving charges. Special relativity provides a deeper understanding of why Maxwell's equations take the form they do. The Doppler effect for light differs from the classical Doppler effect for sound. For sound, the effect depends on the motion of source and observer relative to the medium. For light with no medium, only relative motion matters. The relativistic Doppler formula includes time dilation effects. Light from an approaching source is blue shifted to higher frequencies, while light from a receding source is red shifted. At high speeds, the shift can be dramatic, with visible light shifted into the X-ray or radio portions of the spectrum. This relativistic Doppler effect has practical applications in astronomy. The redshift of distant galaxies reveals their recession velocities, providing evidence for universal expansion. The Doppler broadening of spectral lines indicates the temperature and turbulence in stellar atmospheres. Police radar guns must account for relativistic corrections when measuring the speeds of very fast vehicles, though the corrections are tiny at highway speeds. Special relativity places fundamental limits on information transmission. No signal can travel faster than light, establishing an absolute boundary on how quickly distant parts of the universe can communicate. This light speed limit isn't just about light itself, but about causality. Any faster than light signal would allow information to travel into the past in some reference frames, creating causality paradoxes. These causality constraints have profound implications for our understanding of the universe. They establish the concept of a light cone, the region of spacetime that can causally influence or be influenced by a given event. Your future light cone contains all events you could possibly influence. Your past light cone contains all events that could have influenced you. Events outside your light cone are causally disconnected from you. Special relativity was a triumph, but Einstein recognized its limitations almost immediately. The theory applied only to inertial reference frames, those moving at constant velocity. It couldn't handle acceleration, and more troublingly, it seemed incompatible with Newton's theory of gravity. According to Newton, gravitational effects propagated instantaneously throughout space. If the sun suddenly disappeared, Earth would immediately fly off in a straight line. But special relativity insisted that no influence could travel faster than light. This contradiction demanded resolution. Einstein began working on a generalized theory almost as soon as he completed special relativity. The journey from special to general relativity would take 8 years of intense intellectual effort, false starts, and mathematical struggles that pushed Einstein to his limits. The resulting theory wouldn't just reconcile gravity with relativity, it would completely reimagine gravity not as a force, but as the curvature of spacetime itself. The breakthrough began with what Einstein later called the happiest thought of my life, which occurred in 1907 while he was still working at the patent office. He realized that a person falling freely feels no gravitational force. If you're in a falling elevator and drop an object, it falls alongside you, appearing to float. From your perspective, gravity has been eliminated. Conversely, if you're in a rocket accelerating upward in deep space, you feel pressed to the floor exactly as if you were standing in a gravitational field. Einstein recognized this wasn't just a coincidence, but revealed something fundamental about gravity's nature. This observation led to the equivalence principle, the cornerstone of general relativity. In its simplest form, the equivalence principle states that being at rest in a gravitational field is equivalent to being accelerated in the absence of gravity. No local experiment can distinguish between the two situations. If you're in a windowless room, you can't tell whether you're sitting on Earth's surface or in a rocket accelerating at 9.8 meters per second squared in deep space. The equivalence principle had immediate consequences. Consider a beam of light crossing your accelerating rocket horizontally. From an external inertial perspective, the light travels in a straight line while the rocket accelerates upward. From your accelerated perspective inside the rocket, the light beam curves downward. By the equivalence principle, light must also curve in a gravitational field. Gravity bends light, a prediction that would later provide crucial evidence for general relativity. Time dilation in gravitational fields followed similarly. Imagine a light pulse sent from the bottom to the top of an accelerating rocket. During the light's transit time, the rocket's velocity increases, so the receiver at the top is moving away from the light source faster than when the pulse was emitted. This causes a redshift, lowering the light's frequency. By the equivalence principle, the same must occur in a gravitational field. Light climbing out of a gravitational field is redshifted, which means time runs slower in stronger gravitational fields. These insights were profound, but developing them into a complete theory proved extraordinarily difficult. Einstein needed to describe gravity not as a force, but as a property of spacetime itself. This required mathematics far beyond what he'd learned at the Polytechnic. He needed tensor calculus and differential geometry, mathematical tools for describing curved spaces that had been developed by mathematicians like Riemann, Christoffel, and Ricci, but were unknown to most physicists. Einstein's friend Marcel Grossmann, now a mathematics professor, introduced him to these mathematical tools. Together they worked on what became known as the Entwerth theory, an early attempt at general relativity. This theory had the right general structure, but wasn't quite correct. It took Einstein several more years to identify and fix the problems, years filled with intense calculation, conceptual struggles, and competition from other physicists working on similar ideas. The mathematical challenge was formidable. In special relativity, spacetime is flat, described by the simple Minkowski metric. In general relativity, spacetime is curved, and the metric becomes a complicated function of position. Instead of one metric for all of spacetime, you need different metrics for different regions, smoothly connected. The curvature at each point depends on the matter and energy present there, but the relationship is highly nonlinear. Einstein sought field equations that would relate the geometry of spacetime to its matter-energy content. These equations needed to satisfy several requirements. They should reduce to Newton's gravity in the weak field, low velocity limit. They should be generally covariant, taking the same form in all coordinate systems, not just inertial ones. They should embody the equivalence principle, and they should be consistent with conservation of energy and momentum. By 1913, Einstein had moved to Berlin as a member of the Prussian Academy of Sciences, finally achieving the academic recognition that had long eluded him. Free from teaching obligations, he could focus entirely on research. But progress remained frustratingly slow. He pursued several wrong approaches, at one point convincing himself that generally covariant field equations were impossible. The breakthrough came in November 1915, in a burst of creativity rivaling his miracle year. Einstein realized his earlier reasoning about general covariance was flawed. Working feverishly, he found the correct field equations. In a series of 4 papers, presented weekly to the Prussian Academy, he developed the final theory, applied it to Mercury's orbit, and predicted the bending of starlight by the Sun. The Einstein field equations, the heart of general relativity, are deceptively simple in appearance. R mu nu minus 1/2 g mu nu r plus lambda g mu nu equals 8 pi g over c to the 4th times t mu nu. The left side describes the curvature of spacetime, while the right side describes the energy and momentum content. In words, the equations say that matter energy tells spacetime how to curve, and curved spacetime tells matter how to move. Despite their simple appearance, these are actually 10-coupled, non-linear, partial differential equations, notoriously difficult to solve except in special cases. Each index mu and nu runs over 4 values corresponding to the 4 dimensions of spacetime, but symmetries reduce the 10 independent equations. The equations are non-linear because gravity itself carries energy, which creates more gravity, leading to complex feedback effects. The application to Mercury's orbit provided immediate validation. Astronomers had long known that Mercury's perihelion, its closest approach to the Sun, precessed about 574 arc-seconds per century. Most of this could be explained by the gravitational pull of other planets, but 43 arc-seconds per century remained unexplained. Einstein's theory predicted exactly this amount of additional precession due to the curvature of spacetime near the Sun. When Einstein calculated this result, he was so excited that he had heart palpitations. The prediction of light bending was even more dramatic. Newton's theory, if extended to light, predicted some bending, but general relativity predicted twice as much. A star appearing near the Sun's edge during a solar eclipse should be displaced by about 1.75 arc-seconds. This was measurable with the technology of the time, but it required observing stars near the Sun, which was only possible during a total solar eclipse. World War I delayed the crucial test, but in 1919, Arthur Eddington led expeditions to observe a solar eclipse from Brazil and West Africa. Despite equipment problems and weather challenges, the expeditions obtained photographs showing star positions shifted by amounts consistent with Einstein's prediction. When the results were announced at a joint meeting of the Royal Society and Royal Astronomical Society in London, they created a sensation. The Times of London proclaimed revolution in science and Newton's ideas overthrown. Overnight, Einstein became a global celebrity, his name synonymous with genius. The public was fascinated by the idea that space and time could be curved, even if they didn't understand the details. Einstein's theories seemed to match the spirit of the post-war era, overthrowing old certainties and revealing a stranger, more mysterious universe. His pacifism and internationalism during the war also resonated with those hoping for a more peaceful future. But general relativity's implications went far beyond explaining small anomalies in planetary orbits. The theory fundamentally changed our understanding of gravity. In Newton's picture, gravity was a mysterious force acting instantly across empty space. In Einstein's picture, gravity wasn't a force at all, but the manifestation of curved spacetime. Massive objects warp the geometry of spacetime around them, and objects move along the straightest possible paths through this curved geometry. This geometric interpretation of gravity is beautifully elegant, but deeply counterintuitive. We're accustomed to thinking of geometry as fixed and forces as causing acceleration. General relativity reverses this, making geometry dynamic and eliminating gravitational force. The Earth orbits the Sun not because of an attractive force, but because the Sun's mass curves spacetime, and Earth follows the straightest path through that curved spacetime. To visualize this, though only partially, imagine a stretched rubber sheet. Place a heavy ball in the center, and it creates a depression. Roll a marble near the ball, and it curves around the depression. The marble isn't attracted to the ball, it's following the geometry of the curved surface. This analogy is imperfect, as it uses gravity to explain gravity and only shows spatial curvature, not spacetime curvature, but it captures something of the geometric nature of Einstein's theory. The mathematics of curved spacetime is described by Riemannian geometry, developed decades before Einstein by the mathematician Bernhard Riemann. In flat spacetime, parallel lines never meet. Triangles have angles summing to 180 degrees, and the shortest distance between points is a straight line. In curved spacetime, none of these familiar properties need hold. Parallel lines can converge or diverge, triangles can have angle sums greater or less than 180 degrees, and the shortest paths are curves called geodesics. The curvature of spacetime is characterized by the Riemann curvature tensor, a mathematical object with 20 independent components in 4 dimensions. This tensor encodes all information about how spacetime is curved at each point. Various contractions and traces of this tensor give the Ricci tensor and scalar curvature that appear in Einstein's field equations. The mathematics is formidable, but it precisely captures how matter and energy warp spacetime. General relativity predicted several new phenomena beyond light bending and perihelion precession. Gravitational time dilation, already suggested by the equivalence principle, was a necessary consequence. Clocks run slower in stronger gravitational fields. A clock at sea level runs slightly slower than one on a mountaintop. This effect, though tiny on Earth, becomes extreme near massive objects. Near a black hole's event horizon, time dilation becomes infinite from an external perspective. The theory also predicted gravitational redshift. Light climbing out of a gravitational field loses energy, shifting toward longer, redder wavelengths. This effect was first measured in 1959 by Pound and Rebka using the Mussbauer effect to detect the tiny frequency shift of gamma rays travelling up a tower at Harvard University. The measured shift agreed with Einstein's prediction to within 1%. Perhaps the most spectacular prediction was gravitational waves, ripples in spacetime itself propagating at light speed. When massive objects accelerate, they create distortions in spacetime that spread outward, like waves on a pond. These waves alternately stretch and compress space as they pass, though the effect is incredibly tiny. Einstein himself doubted they could ever be detected, and it would take a century before technology advanced enough to observe them directly. General relativity also revealed that the universe itself could be dynamic. Einstein's equations applied to the universe as a whole suggested it should be either expanding or contracting. This troubled Einstein, who believed in a static, eternal universe. He added a cosmological constant term to his equations to allow for a static solution. When Edwin Hubble discovered universal expansion in 1929, Einstein called the cosmological constant his biggest blunder. Ironically, modern observations of accelerating expansion have revived the cosmological constant in the form of dark energy. The theory predicted exotic objects that seemed too strange to exist in nature. If enough mass was compressed into a small enough region, space-time curvature would become so extreme that not even light could escape. These objects, later called black holes, were implicit in Carl Schwarzschild's 1916 solution to Einstein's equations, found while Schwarzschild was serving on the Russian front during World War I. For decades, most physicists, including Einstein, believed black holes were mathematical curiosities that wouldn't form in reality. General relativity changed our understanding of the universe's large-scale structure and evolution. The theory provided the framework for modern cosmology, describing how the universe has expanded and evolved since the Big Bang. It predicts the existence of gravitational lensing, where massive objects bend light from distant sources, creating multiple images or distorted arcs. This effect, now routinely observed, has become a crucial tool for mapping dark matter and studying distant galaxies. The theory's mathematical beauty attracted many physicists. The way complex physical phenomena emerged from elegant geometric principles seemed to reveal something deep about nature's structure. David Hilbert, the great mathematician, independently derived similar field equations at nearly the same time as Einstein, though he acknowledged Einstein's priority. The theory inspired attempts to geometrize other forces, a program that continues today in string theory and other approaches to quantum gravity. To truly appreciate general relativity, we must delve into the remarkable geometry that underlies it. The idea that space and time form a curved four-dimensional manifold is so far from everyday experience that it challenges our ability to visualize and comprehend. Yet this geometric framework isn't just mathematical abstraction. It describes the actual structure of the universe we inhabit. In our everyday experience, space appears flat and three-dimensional, obeying the rules of Euclidean geometry we learned in school. Parallel lines never meet. The angles of a triangle sum to exactly 180 degrees, and the circumference of a circle equals 2 pi times its radius. These properties seem so fundamental that for over 2,000 years, mathematicians believed they were logical necessities. But in the 19th century, mathematicians like Gauss, Bolyai, Lobachevsky, and Riemann discovered that perfectly consistent geometries could exist that violated these familiar rules. Curved spaces can have positive curvature, like the surface of a sphere, or negative curvature, like a saddle shape. On a sphere's surface, initially parallel lines converge, triangles have angle sums greater than 180 degrees, and circles have circumferences less than 2 pi times their radius. On a negatively curved surface, parallel lines diverge. Triangles have angle sums less than 180 degrees, and circles have circumferences greater than 2 pi times their radius. These examples involve two-dimensional surfaces curved in three-dimensional space, which we can visualize. But general relativity requires us to think about four-dimensional space-time that's curved without being embedded in a higher dimensional flat space. This intrinsic curvature is harder to visualize but mathematically well defined. The curvature exists as a property of the space itself, not requiring an external space to curve into. To understand intrinsic curvature, imagine intelligent two-dimensional beings living on a curved surface, unable to perceive the third dimension. They could still detect their surface's curvature through measurements entirely within their two-dimensional world. They might notice that large triangles have angle sums different from 180 degrees, or that the ratio of a circle's circumference to its radius differs from 2 pi. These deviations from Euclidean geometry reveal curvature without reference to an embedding space. Similarly, we three-dimensional beings embedded in four-dimensional spacetime can detect spacetime curvature through measurements within our accessible dimensions. We observe light bending near massive objects, clocks running at different rates in gravitational fields, and the precession of planetary orbits. These effects reveal that our spacetime is curved, even though we can't step outside it to see the curvature directly. The mathematics of curved spacetime uses the concept of a metric, which defines distances between nearby points. In flat spacetime, the metric is simple, given by the Minkowski metric of special relativity. In curved spacetime, the metric becomes a complicated function of position, encoding how distances and time intervals are measured at each point. The metric contains all information about the geometry of spacetime. Consider how we measure distance on Earth's curved surface. The straight-line distance through Earth's interior between two cities isn't accessible to surface dwellers. Instead, we measure distance along the curved surface following great circles. Similarly, in curved spacetime, we measure intervals along the curved geometry, not through some inaccessible flat embedding space. The metric tells us how to calculate these measurements. The components of the metric tensor, usually denoted GA mu nu, form a 4x4 symmetric matrix at each point in spacetime. In flat spacetime, this matrix is diagonal with entries of plus or minus 1, depending on the signature convention. In curved spacetime, the components become functions of position, and off-diagonal terms can appear. These 10 independent components completely specify the geometry at each point. From the metric, we can derive the Christoffel symbols, which describe how vectors change when parallel transported through curved spacetime. Parallel transport is a way of moving vectors along curves while keeping them as parallel as possible. In flat space, parallel transported vectors maintain their direction. In curved space, they rotate relative to coordinate axes, and this rotation reveals the curvature. The Riemann curvature tensor, constructed from derivatives of the Christoffel symbols, provides a complete description of spacetime curvature. This tensor has 20 independent components in 4 dimensions, encoding how spacetime is curved in every possible direction at each point. It's a formidable mathematical object, but it precisely captures all aspects of curvature. Different contractions of the Riemann tensor yield simpler curvature measures. The Ricci tensor, obtained by contracting two indices, describes how volumes change in curved spacetime. The Ricci scala, a further contraction, gives a single number, characterizing the overall curvature at each point. These appear in Einstein's field equations relating curvature to matter-energy content. Tidal forces provide an intuitive way to understand space-time curvature. In Newtonian gravity, tidal forces arise because gravitational fields vary with position. Objects closer to a massive body experience stronger gravity than those farther away, creating stretching and squeezing forces. In general relativity, these tidal forces are manifestations of space-time curvature. The Riemann tensor precisely describes these tidal effects. Imagine falling feet first toward Earth. Your feet, being closer to Earth, experience stronger gravity than your head, creating a stretching force along your body. Simultaneously, your left and right sides are pulled toward Earth's center, creating a squeezing force. These tidal forces would exist even in a freely falling reference frame where you feel weightless. They reveal the curvature of spacetime that can't be eliminated by choice of reference frame. The equivalence principle states that gravity can be locally eliminated by choosing a freely falling reference frame. But this elimination is only local. Over extended regions, tidal forces reveal spacetime curvature that no choice of coordinates can remove. This distinction between local and global properties is crucial in general relativity. Locally, spacetime always looks flat, but globally, curvature manifests through tidal effects and the failure of initially parallel geodesics to remain parallel. Geodesics, the straightest possible paths through curved spacetime, replace the straight lines of flat space. A geodesic is the path followed by a freely falling particle, experiencing no forces except gravity. In spacetime, geodesics maximize the proper time between events, the time measured by a clock following that path. This variational principle, analogous to Fermat's principle in optics, provides an elegant way to derive particle trajectories. The geodesic equation derived from the metric describes how particles move through curved spacetime. It shows that what we perceive as gravitational acceleration is actually the result of following a straight path through curved geometry. An orbiting planet isn't pulled by a gravitational force but follows a geodesic through the curved spacetime around the Sun. The curvature of spacetime, not a force, determines the motion. This geometric view of gravity has profound implications. In Newton's theory, gravity is a force that can be shielded or counteracted. In Einstein's theory, gravity is geometry itself, as inescapable as the structure of space and time. You can no more shield against gravity than you can shield against the curvature of Earth's surface. This geometric nature explains why all objects fall at the same rates in a gravitational field, a fact that seemed coincidental in Newtonian physics but is necessary in general relativity. The curvature of spacetime affects not just particle trajectories, but all physical processes. Light rays follow null geodesics, paths of zero spacetime interval. The bending of light near massive objects isn't due to light having mass, but to light following the straightest available path through curved spacetime. Electromagnetic waves propagating through curved spacetime experience frequency shifts and polarization changes. Even quantum mechanical wave functions are affected by spacetime curvature. Different types of matter and energy curve spacetime in characteristic ways. A spherically symmetric mass like a star creates the Schwarzschild geometry, with curvature decreasing with distance. A rotating mass produces the Kerr geometry, which drags spacetime around with it, an effect called frame dragging. Electromagnetic fields, pressure, and momentum all contribute to spacetime curvature through the stress-energy tensor. The stress-energy tensor, appearing on the right side of Einstein's field equations, encodes all sources of spacetime curvature. Its components include energy density, momentum density, pressure, and stress. The conservation of this tensor, required by the mathematical structure of general relativity, ensures local conservation of energy and momentum even in curved spacetime. This connection between geometry and conservation laws reveals deep relationships in physics. Space-time curvature can vary dramatically in scale and intensity. Near Earth's surface, the curvature is tiny, causing time to run about 1 part in a billion slower than in deep space. Near a neutron star, curvature becomes extreme, with time running noticeably slower and space significantly distorted. At a black hole's event horizon, curvature effects become infinite from an external perspective, creating a boundary from which nothing can escape. The global topology of spacetime, distinct from its local curvature, presents fascinating possibilities. Spacetime could be finite but unbounded, like the surface of a sphere but in 4 dimensions. It could have non-trivial topology, with handles or holes that create multiple paths between events. Wormholes, hypothetical shortcuts through spacetime, would represent extreme topological structures, though their physical existence remains speculative. Cosmological models describe the large-scale geometry of the universe. The Friedmann-Lemaitre-Robertson-Walker metric describes a homogeneous, isotropic universe that can be positively curved, negatively curved, or flat. Current observations suggest our universe is remarkably close to flat on large scales, with any curvature being extremely small. This flatness is one of the puzzles that inflation theory attempts to explain. The dynamic nature of spacetime geometry distinguishes general relativity from earlier theories. Spacetime isn't a fixed stage but an active participant in physics. Gravitational waves are ripples in spacetime geometry itself, propagating at light speed. When massive objects accelerate, they create distortions that spread outward, alternately stretching and compressing space as they pass. These waves carry energy away from their sources, causing orbital decay in binary systems. The detection of gravitational waves by LIGO in 2015 confirmed one of general relativity's most spectacular predictions. The detectors measured distance changes of less than 1/10,000th the width of a proton as gravitational waves from colliding black holes passed through Earth. This achievement required understanding spacetime geometry with extraordinary precision and developing technology to measure incredibly tiny effects. The interaction between quantum mechanics and curved spacetime creates new phenomena. Quantum field theory in curved spacetime predicts particle creation in strong gravitational fields. The Unruh effect suggests that accelerated observers see a thermal bath of particles where inertial observers see vacuum. Hawking radiation, the theoretical emission from black holes, arises from quantum effects near the event horizon. These phenomena hint at deep connections between gravity, thermodynamics, and quantum mechanics. Understanding curved spacetime geometry has practical applications. GPS satellites must account for both special relativistic effects due to their motion and general relativistic effects due to Earth's gravity. Without these corrections, GPS positions would drift by about 10 kilometers per day. Gravitational lensing is used to map dark matter in galaxy clusters and discover distant exoplanets. Even the precession of satellite orbits due to frame dragging has been measured, confirming another prediction of general relativity. The mathematical beauty of general relativity's geometric framework has inspired physicists for over a century. The way physical phenomena emerge from geometric principles suggests that geometry might be more fundamental than force. This has motivated attempts to geometrize other interactions, from Kaluza-Klein theory's extra dimensions to modern string theory's complex geometries. Whether all of physics can be understood geometrically remains an open question. The history of general relativity's experimental verification is a testament to human ingenuity and technological progress. From the first confirmations using telescopes and photographic plates to modern experiments with laser interferometers and atomic clocks. Each test has pushed the boundaries of precision measurement. These experiments haven't just confirmed Einstein's theory, they've revealed the extraordinary accuracy with which general relativity describes gravitational phenomena across an enormous range of scales. The first great triumph came even before the theory was complete. The anomalous precession of Mercury's perihelion had puzzled astronomers for decades. After accounting for perturbations from all known planets, Mercury's orbit still precessed an extra 43 arc-seconds per century. Various explanations had been proposed, including an undiscovered planet called Vulcan orbiting closer to the Sun, modifications to Newton's inverse square law, and even a slightly oblate Sun. None proved satisfactory. When Einstein applied his developing theory to Mercury's orbit in November 1915, he found it predicted exactly the observed excess precession. The calculation was straightforward once the field equations were known, requiring only the Schwarzschild solution for a spherically symmetric mass. The agreement was perfect within observational uncertainty. Einstein later recalled being so excited by this result that he had heart palpitations for days. This wasn't just solving a puzzle, it was confirmation that his radical reconception of gravity was correct. The bending of starlight by the sun provided a more dramatic test. Einstein's theory predicted that light passing near the sun would be deflected by about 1.75 arc-seconds at the sun's limb, twice the value that Newtonian theory might suggest if light were affected by gravity. This deflection could only be observed during a total solar eclipse when stars near the sun became visible. The effect was tiny, requiring careful photographic measurements and comparison with the stars' positions when the sun was elsewhere in the sky. Arthur Eddington, a British astrophysicist who was among the first to understand general relativity, organised expeditions to observe the May 29th, 1919 solar eclipse. 2 teams travelled to Sobral in Brazil and Principe off the African coast. The expeditions faced numerous challenges: equipment problems, weather uncertainties, and the need to transport delicate instruments to remote locations all threatened the observations. The Principe team dealt with clouds that cleared only briefly during totality. When the photographic plates were analysed, they showed stellar deflections consistent with Einstein's prediction, though the uncertainty was considerable. Eddington's announcement of the results at a joint meeting of the Royal Society and Royal Astronomical Society on November 6, 1919, created a sensation. The Times of London proclaimed "revolution in science" and Newtonian ideas overthrown. Einstein became an international celebrity overnight, his theory confirmed by British scientists just after a devastating war between their nations. Some historians have questioned whether the 1919 measurements were really precise enough to distinguish between Einstein's prediction and alternatives. The data analysis involved subjective decisions about which plates to trust and how to weight different measurements. But subsequent eclipse expeditions and modern measurements using radio astronomy have confirmed the light deflection to high precision. The deflection of radio waves from quasars by the sun, measurable without waiting for eclipses, now agrees with general relativity to better than 0.1%. Gravitational redshift, the change in light frequency as it climbs out of or falls into a gravitational field, provided another early test. Light escaping from a massive object loses energy and shifts toward longer, redder wavelengths. The effect near Earth's surface is tiny, only about 1 part in a billion, but it's measurable with precise spectroscopy. Early attempts to measure the gravitational redshift of light from white dwarf stars gave results roughly consistent with predictions but with large uncertainties. The first precise terrestrial test came from the Pound-Rebka experiment in 1959. Robert Pound and Glenn Rebka used the Nussbauer effect, which produces gamma rays with extremely well-defined frequencies, to measure the gravitational redshift over a height of just 22.5 meters in Harvard's Jefferson Tower. The frequency shift was only about 2 parts in 10 to the 15th, but the Nussbauer effect allowed such precise measurements that they confirmed Einstein's prediction to within 1%. Later experiments improved this precision dramatically. In 1976, the Gravity Probe A experiment flew a hydrogen-mass atomic clock on a suborbital rocket to an altitude of 10,000 kilometers. Comparing its frequency with identical clocks on the ground confirmed gravitational redshift to about 0.007% precision. Modern tests using atomic clocks and GPS satellites routinely verify gravitational time dilation to extraordinary accuracy. The Global Positioning System provides continuous confirmation of both special and general relativistic effects. GPS satellites orbit at about 20,000 kilometers altitude, where Earth's gravitational field is weaker than at the surface. This causes satellite clocks to run about 45 microseconds per day, faster than Earth clocks, due to gravitational time dilation. Additionally, the satellite's orbital velocity of about 14,000 kilometers per hour causes them to run about 7 microseconds per day, slower, due to special relativistic time dilation. The net effect is that satellite clocks run 38 microseconds per day fast. Without correcting for these relativistic effects, GPS positions would accumulate errors of about 10 kilometers per day. The system's ability to determine positions to within meters requires accounting for relativity with nanosecond precision. Every GPS receiver effectively performs a relativity experiment, confirming Einstein's theories millions of times daily. This practical application demonstrates that relativity isn't just abstract theory, but essential for modern technology. Frame dragging, the phenomenon where rotating masses drag space-time around with them, was predicted by general relativity, but is extraordinarily weak near Earth. The Gravity Probe B experiment, launched in 2004 after decades of development, attempted to measure this effect using ultra-precise gyroscopes orbiting Earth. The experiment faced enormous technical challenges, requiring the most perfect spheres ever manufactured and isolation from all non-gravitational disturbances. After years of data analysis to remove systematic errors, Gravity Probe B confirmed frame dragging to about 19% precision, consistent with general relativity's predictions. While less precise than hoped, this was the first direct measurement of how rotating masses twist space-time. The LAGEOS satellites, tracked by laser ranging, have also shown evidence of frame dragging through subtle changes in their orbits, confirming the effect to better precision. Binary pulsars have provided some of the most stringent tests of general relativity in strong gravitational fields. Pulsars are neutron stars emitting regular radio pulses, acting as extraordinarily precise cosmic clocks. When pulsars orbit other compact objects, their orbital dynamics test general relativity in regimes far stronger than anything accessible in the solar system. The Hulse-Taylor binary pulsar, discovered in 1974, consists of 2 neutron stars orbiting each other every 7.75 hours. General relativity predicts that this system should lose energy through gravitational wave emission, causing the orbit to decay. Decades of precise timing measurements have shown the orbital period decreasing at exactly the rate predicted by Einstein's theory, providing indirect evidence for gravitational waves and earning Russell Hulse and Joseph Taylor the 1993 Nobel Prize in Physics. The double pulsar system PSR J0737-3039, discovered in 2003, provides even more stringent tests. With both neutron stars visible as pulsars, astronomers can measure multiple relativistic effects simultaneously. The system tests general relativity in the strong field regime to better than 0.05% precision, the most accurate confirmation of the theory in strong gravity. These measurements constrain alternative theories of gravity and demonstrate general relativity's validity even in extreme conditions. Gravitational lensing has become a powerful tool for both testing relativity and studying the universe. When light from a distant source passes near a massive object, the curved space-time acts like a lens, bending and focusing the light. This can create multiple images of the same object, Einstein rings where the source appears as a circle around the lens, or subtle distortions in the shapes of background galaxies. The first gravitational lens was discovered in 1979 when astronomers found two quasars with identical spectra and redshifts but slightly different positions. They realized they were seeing two images of the same quasar, with light bent by an intervening galaxy. Since then, hundreds of gravitational lenses have been discovered. The detailed properties of these lenses, including image positions, magnifications, and time delays between images, match general relativity's predictions precisely. Weak gravitational lensing, the subtle distortion of distant galaxy shapes by intervening matter, has become crucial for mapping dark matter. By statistically analyzing the shapes of millions of galaxies, astronomers can reconstruct the distribution of matter, including invisible dark matter, between us and the distant galaxies. This technique has revealed the cosmic web's structure and provided evidence for dark energy's existence. Gravitational microlensing occurs when a compact object passes between us and a background star, temporarily magnifying the star's light. This effect has been used to discover thousands of exoplanets, including some too small to detect by other methods. The detailed light curves of microlensing events match general relativity's predictions, confirming the theory's accuracy for yet another phenomenon. Black holes, once considered too exotic to exist in nature, have become central to testing general relativity in extreme conditions. While we can't observe black holes directly, we can see their effects on surrounding matter. Gas falling into black holes forms accretion disks that heat up and emit X-rays. The properties of these emissions, including quasi-periodic oscillations and ion line profiles, match predictions from general relativity in strong gravitational fields. The orbits of stars around the supermassive black hole at our galaxy's centre provide another spectacular test. Decades of observations have tracked individual stars orbiting at speeds up to 8,000 kilometers per second, approaching within a few hundred astronomical units of the black hole. These orbits show relativistic precession consistent with general relativity's predictions. The star S2, with a 16-year orbit, has been tracked through multiple orbits, confirming gravitational redshift and orbital precession at the few percent level. The Event Horizon, telescope's image of the supermassive black hole in galaxy M87, released in 2019, provided visual confirmation of general relativity's predictions. The glowing ring of hot gas surrounding the black hole's shadow matches the size and shape predicted by the Kerr metric for a rotating black hole. Detailed analysis of the image's structure confirms general relativity's description of light propagation near black holes. Perhaps the most spectacular confirmation came with a direct detection of gravitational waves. These ripples in spacetime, predicted by Einstein in 1916, are produced when massive objects accelerate. But the effect is so weak that Einstein himself doubted they could ever be detected. A passing gravitational wave stretches and compresses space by incredibly tiny amounts, typically less than the width of an atomic nucleus, even for violent cosmic events. The Laser Interferometer Gravitational Wave Observatory, LIGO, achieved the seemingly impossible. Using laser interferometry to measure distance changes between mirrors 4 kilometers apart, LIGO can detect changes smaller than 1/10,000th the width of a proton. This required isolating the mirrors from all vibrations, using multiple stages of suspension, active feedback systems, and operating in vacuum. On September 14, 2015, LIGO detected gravitational waves from 2 black holes merging 1.3 billion light-years away. The signal, lasting just 0.2 of a second, matched general relativity's predictions for the inspiral merger and ring-down of a black hole binary. The detection confirmed gravitational waves' existence, validated general relativity in the strong field regime, and opened an entirely new way of observing the universe. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events from merging black holes and neutron stars. Each detection tests general relativity in slightly different ways. The wave's propagation speed has been confirmed to equal light speed to extraordinary precision. The waveforms match numerical relativity simulations based on Einstein's equations. No deviations from general relativity have been found, even in the extreme conditions of black hole mergers. The detection of gravitational waves from a binary neutron-star merger in August 2017 was particularly significant. This event, GRB 170817, was also observed electromagnetically as a gamma-ray burst and kilonova. The near-simultaneous arrival of gravitational waves and electromagnetic radiation, after travelling 130 million light-years, confirmed that gravitational waves travel at light speed to within 1 part in 10 to the 15th. This multi-messenger observation inaugurated a new era in astronomy. Tests of general relativity continue to improve in precision and explore new regimes. Pulsar timing arrays search for nanohertz gravitational waves from supermassive black hole binaries. Next-generation gravitational wave detectors will test general relativity with even greater precision. Observations of black hole shadows, orbital dynamics near compact objects, and cosmological phenomena all provide opportunities to test Einstein's theory in new ways. Alternative theories of gravity make different predictions that can be tested experimentally. Some predict violations of the equivalence principle, variations in fundamental constants, or additional polarization states for gravitational waves. So far, every test has confirmed general relativity and ruled out or constrained alternatives. But physicists continue searching for deviations that might point toward a quantum theory of gravity or reveal new physics. The agreement between general relativity's predictions and observations is remarkable. From the solar system to cosmological scales, from weak fields near Earth to strong fields near black holes, from slow velocities to near light speed, Einstein's theory has passed every test. The precision of some confirmations is extraordinary, agreeing with predictions to better than 1 part in 10,000. This success across such a vast range of phenomena makes general relativity one of the best tested theories in physics. Black holes represent the most extreme predictions of general relativity, regions where space-time curvature becomes so intense that the known laws of physics reach their limits. These objects, once dismissed as mathematical curiosities too bizarre to exist in nature, have become central to our understanding of the universe. From stellar mass black holes formed in supernovae to supermassive giants anchoring galaxies, black holes reveal the full implications of Einstein's geometric theory of gravity. The concept of an object so massive that not even light could escape predates general relativity. In 1783, John Michell, an English natural philosopher, calculated that a star 500 times the Sun's radius but with the same density, would have an escape velocity exceeding light speed. Pierre-Simon Laplace made similar calculations in 1796. These dark stars were based on Newtonian gravity and the corpuscular theory of light, but they hinted at the possibility of invisible, massive objects. The modern understanding of black holes emerged from Karl Schwarzschild's solution to Einstein's field equations. In 1916, while serving on the Russian front during World War I, Schwarzschild found the first exact solution describing the spacetime geometry around a spherically symmetric mass. His solution revealed something remarkable. At a certain radius, later called the Schwarzschild radius, the metric components became singular. For a mass m, this radius equals 2gm/c squared, where g is Newton's gravitational constant. At first, physicists believed this Schwarzschild singularity was a mathematical artifact that could be removed by choosing different coordinates. Einstein himself never accepted that such objects could form in nature. In 1939, he published a paper attempting to prove that matter couldn't collapse beyond a certain point. But that same year, Robert Oppenheimer and Hartland Snyder showed that a sufficiently massive star undergoing gravitational collapse would indeed form what we now call a black hole. The term black hole wasn't coined until 1967 by John Wheeler, replacing earlier terms like frozen star or collapsed star. Wheeler's evocative name captured both the object's defining characteristic, that nothing can escape, and the mystery surrounding these extreme objects. The name stuck and entered popular culture, making black holes perhaps the most famous prediction of general relativity. Understanding black hole structure requires careful analysis of the Schwarzschild metric and its extensions. The event horizon, located at the Schwarzschild radius, marks the point of no return. Anything crossing the event horizon, whether matter, light, or information, is inexorably drawn toward the singularity at the centre. From outside, the event horizon appears as a perfectly black sphere, absorbing all incident radiation without reflection or emission. The geometry of spacetime near a black hole is profoundly warped. As you approach the event horizon, spacetime curvature increases without bound. Tidal forces, the differential gravitational pull across an extended object, become extreme. An astronaut falling feet first toward a stellar mass black hole would experience spaghettification, being stretched vertically and compressed horizontally by tidal forces that would eventually tear apart even atomic nuclei. Time dilation near black holes reaches extreme levels. As seen from far away, clocks near the event horizon run arbitrarily slowly. An outside observer watching someone fall into a black hole would see them approach the horizon ever more slowly, their image redshifting and fading, but never quite crossing the horizon. From the falling person's perspective, however, they cross the horizon in finite proper time, noticing nothing special at the moment of crossing. This dichotomy between external and infalling perspectives highlights the importance of coordinate systems in general relativity. The Schwarzschild coordinates, natural for distant observers, become singular at the horizon. But other coordinate systems, like Eddington-Finkelstein or Kruskal-Szekeres coordinates, remain well behaved at the horizon, revealing it as a coordinate singularity rather than a physical one. The true physical singularity lies at the centre, where spacetime curvature becomes infinite. Rotating black holes, described by the Kerr metric discovered by Roy Kerr in 1963, are even more complex. Rotation drags spacetime around the black hole, creating an ergosphere outside the event horizon where nothing can remain stationary relative to distant stars. Objects in the ergosphere are forced to rotate with the black hole, though they can still escape. The Kerr metric predicts that rotating black holes have ring-shaped singularities rather than point singularities, though the physical interpretation remains unclear. The Penrose process, proposed by Roger Penrose in 1969, shows that rotational energy can be extracted from a Kerr black hole by splitting a particle in the ergosphere and allowing one piece to fall into the black hole while the other escapes. Energy greater than the original particle's energy can be extracted. This process reduces the black hole's angular momentum, suggesting that rotating black holes might power some of the universe's most energetic phenomena. Charged black holes, described by the Reissner-Nordström metric, add another layer of complexity. These solutions predict multiple horizons and the theoretical possibility of avoiding the singularity, though such objects are unlikely in nature, since any significant charge would quickly be neutralized by attracting opposite charges from the surrounding plasma. The most general black hole solution, the Kerr-Newman metric, describes rotating charged black holes, though only mass and angular momentum are likely relevant for astrophysical black holes. The no-hair theorem, developed in the 1960s and 70s, states that black holes are characterized by only three properties: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole is lost behind the event horizon. This represents an enormous loss of information, as a black hole formed from hydrogen gas is identical to one formed from iron or antimatter if their mass, spin, and charge are the same. Black hole thermodynamics, developed by Jacob Bekenstein and Stephen Hawking in the 1970s, revealed unexpected connections between gravity, quantum mechanics, and thermodynamics. Bekenstein proposed that black holes have entropy proportional to their surface area, not their volume. This was puzzling since entropy usually scales with volume, but it suggested that information in a black hole is somehow encoded on its two-dimensional surface, rather than in its three-dimensional volume. Hawking's discovery of black hole radiation in 1974 revolutionized our understanding. By applying quantum field theory to curved space-time near black holes, Hawking showed that black holes emit thermal radiation with a temperature inversely proportional to their mass. This Hawking radiation causes black holes to slowly evaporate, with smaller black holes radiating faster than larger ones. A black hole with the Sun's mass would take 10 to the 67th years to evaporate, far longer than the current age of the universe. The information paradox, arising from Hawking radiation, remains one of the deepest puzzles in physics. If black holes evaporate completely through thermal radiation, what happens to the information that fell in? Quantum mechanics requires information conservation, but Hawking radiation appears thermal and random, containing no information about what formed the black hole. Various solutions have been proposed, including black hole complementarity, the holographic principle, and firewalls, but no consensus exists. Observational evidence for black holes has accumulated steadily since the 1970s. Cygnus X1, discovered in 1964, was the first strong black hole candidate. This X-ray source is a binary system where a blue supergiant star orbits an invisible companion of about 15 solar masses, well above the maximum mass for a neutron star. The X-rays come from gas stripped from the visible star and heated as it spirals into the black hole. Supermassive black holes, millions to billions of times the Sun's mass, lurk at the centres of most galaxies. The evidence comes from observing stars and gas orbiting at tremendous speeds around invisible central masses. In our Milky Way, decades of observations have tracked individual stars orbiting the galactic centre, revealing a dark object of 4 million solar masses in a region smaller than our solar system. No known alternative to a black hole can explain such observations. Active galactic nuclei, including quasars, blazars, and Seyfert galaxies, are powered by supermassive black holes accreting matter. As gas spirals into these black holes, it forms an accretion disk heated to millions of degrees by friction and compression. These disks can outshine entire galaxies, making quasars visible across billions of light years. Jets of plasma, accelerated to near light speed by magnetic fields threading the disk and black hole, extend for millions of light years in some cases. The merger of black holes produces gravitational waves detectable by LIGO and Virgo. These observations provide direct evidence for black holes and test general relativity in the strong field regime. The merger process follows 3 stages: in spiral, where the black holes orbit ever faster as gravitational waves carry away energy; merger, where the horizons touch and combine; and ring down, where the merged black hole settles into a stationary state. The gravitational wave signal encodes the masses and spins of the merging black holes. Intermediate mass black holes, hundreds to thousands of solar masses, remain elusive but are likely to exist. They might form from the collapse of very massive first-generation stars or through runaway stellar collisions in dense star clusters. Some ultraluminous X-ray sources might harbour intermediate mass black holes, bridging the gap between stellar mass and supermassive black holes. Primordial black holes, formed in the early universe rather than from stellar collapse, remain hypothetical but could contribute to dark matter. Density fluctuations in the extremely early universe might have collapsed directly to black holes without first forming stars. These could have any mass, from microscopic to supermassive, depending on when they formed. Searches for primordial black holes use gravitational microlensing, gravitational waves, and other techniques. The Event Horizon Telescope has provided direct images of black hole shadows. The glowing ring in the image of M87's supermassive black hole corresponds to light from the hot accretion disk, lensed by the black hole's gravity. The dark centre is the black hole's shadow, about 2.5 times larger than the event horizon, due to light bending. These images confirm general relativity's predictions and provide new ways to measure black hole properties. Black holes challenge our understanding of fundamental physics. At the singularity, general relativity predicts infinite curvature, signalling the theory's breakdown. A quantum theory of gravity is needed to understand what really happens at the centre of black holes. String theory, loop quantum gravity, and other approaches attempt to resolve the singularity, possibly replacing it with a quantum fuzz or bounce. The holographic principle, inspired by black hole thermodynamics, suggests that all information in a volume can be encoded on its boundary. This radical idea implies that our 3-dimensional world might be a projection of information stored on a distant 2-dimensional surface. If true, it would fundamentally change our understanding of space, gravity, and quantum mechanics. Wormholes' hypothetical shortcuts through space-time are related to black holes in general relativity's mathematics. The maximally extended Schwarzschild solution includes an Einstein-Rosen bridge connecting 2 asymptotic regions. However, these wormholes are unstable and non-traversable. Exotic matter with negative energy density would be required to hold a wormhole open, and no such matter is known to exist. Black holes might provide insights into quantum gravity. The black hole information paradox forces us to confront the incompatibility between general relativity and quantum mechanics. The microscopic structure of black holes, possibly involving quantum geometry or string theory, might reveal how space-time itself emerges from more fundamental quantum degrees. A freedom firewall paradox, proposed in 2012, sharpened the information paradox further. If information escapes from black holes to preserve unitarity, then the entanglement structure near the horizon must be dramatically different than general relativity suggests. This might require a firewall of high-energy particles at the horizon, contradicting the equivalence principle's prediction that infalling observers experience nothing special when crossing the horizon. The paradox highlights deep tensions between quantum mechanics, general relativity, and thermodynamics. Recent theoretical developments suggest that quantum effects might become important even outside the event horizon. The stretched horizon paradigm places the quantum degrees of freedom just outside the classical horizon, where infalling observers would encounter them before crossing. This quantum atmosphere might encode the information about everything that has fallen into the black hole, providing a mechanism for information preservation without violating causality. Black holes serve as theoretical laboratories for testing ideas about quantum gravity. Their extreme conditions probe the limits of our theories, revealing inconsistencies and pointing toward new physics. The fact that black holes have temperature and entropy suggests deep connections between gravity, thermodynamics, and information theory that we're only beginning to understand. These connections might be crucial for developing a complete theory of quantum gravity. General relativity transformed cosmology from philosophical speculation into quantitative science. Before Einstein, the universe's large-scale structure and evolution were matters of metaphysics rather than physics. Newton's infinite static universe faced theoretical problems like Olber's paradox, questioning why the night sky is dark if stars extend infinitely. Einstein's theory provided the mathematical framework to describe the universe as a whole, leading to revolutionary discoveries about cosmic expansion, the Big Bang, and the universe's ultimate fate. Einstein himself initially resisted the cosmological implications of his theory. When he first applied general relativity to the universe in 1917, he assumed it must be static and eternal, reflecting the prevailing philosophical prejudices. But his equations indicated that a static universe filled with matter would be unstable, either expanding or contracting. To prevent this, Einstein added a cosmological constant term to his field equations, representing a repulsive force that could balance gravitational attraction. This cosmological constant, denoted by lambda, modified the field equations to include a term proportional to the metric itself. Einstein adjusted its value to allow for a static, closed universe of finite size but without boundaries, like the three-dimensional surface of a four-dimensional sphere. This Einstein static universe was unstable, as Arthur Eddington later showed. Any small perturbation would cause it to either expand or contract indefinitely. Alexander Friedmann, a Russian mathematician and meteorologist, took a different approach in 1922. He solved Einstein's equations for a homogeneous isotropic universe without assuming it was static. Friedmann found solutions describing universes that expanded from an initial singularity, reached maximum size, then contracted back to a singularity. Other solutions expanded forever, either from finite or infinite initial size. These Friedmann equations became the foundation of modern cosmology. Einstein initially dismissed Friedmann's work, claiming it contained mathematical errors. After Friedmann demonstrated his calculations were correct, Einstein acknowledged the mathematical validity but doubted the physical relevance. The idea of an expanding universe seemed too radical. Friedmann died in 1925 before his ideas gained acceptance, but his equations would prove prophetic. Georges Lemaitre, a Belgian priest and physicist, independently derived similar solutions in 1927. Going beyond Friedmann, Lemaitre connected the expanding universe model to astronomical observations. He proposed that the universe began from a primeval atom or cosmic egg that exploded, creating space and time. This was the first articulation of what would become the Big Bang theory, though Lemaitre called it the hypothesis of the primeval atom. The observational revolution came from Edwin Hubble's work at Mount Wilson Observatory. Using Cepheid variable stars as distance indicators, Hubble determined that many nebulae were actually independent galaxies far beyond the Milky Way. More remarkably, he found that most galaxies showed red-shifted spectra, indicating they were moving away from us. In 1929, Hubble announced his discovery that galactic redshift increased linearly with distance, implying universal expansion. Hubble's law, stating that recession velocity equals the Hubble constant times distance, provided the first observational evidence for cosmic expansion. The Hubble constant's value, now measured at about 70 kilometers per second per megaparsec, tells us the expansion rate. Tracing this expansion backward implied the universe had a beginning, a moment when all matter and energy were concentrated at infinite density. This Big Bang occurred approximately 13.8 billion years ago. Einstein called the cosmological constant his biggest blunder after learning of cosmic expansion, believing he had missed predicting one of the universe's most fundamental properties. Ironically, observations at the end of the 20th century would resurrect the cosmological constant in the form of dark energy, making Einstein's blunder prescient rather than mistaken. The Big Bang model, developed through the mid-20th century, combined general relativity with nuclear physics and thermodynamics to describe the universe's evolution. In the beginning, the universe was incredibly hot and dense, filled with a soup of fundamental particles. As it expanded and cooled, protons and neutrons formed, then light nuclei through primordial nucleosynthesis. After about 380,000 years, the universe cooled enough for atoms to form, releasing the cosmic microwave background radiation we observe today. This cosmic microwave background, discovered accidentally by Arno Penzias and Robert Wilson in 1964, provides stunning confirmation of the Big Bang model. This radiation, now cooled to about 2.7 Kelvin, fills the universe uniformly, with tiny fluctuations that seeded the formation of galaxies and large-scale structure. Detailed measurements by satellites like COBE, WMAP, and Planck have mapped these fluctuations, revealing the universe's age, composition, and geometry with extraordinary precision. General relativity predicts that the universe's geometry depends on its total energy density. If the density exceeds a critical value, space has positive curvature like a sphere's surface, and the universe is closed and finite. If the density equals the critical value, space is flat and infinite. If the density is below critical, space has negative curvature like a saddle and is infinite. Observations indicate our universe is remarkably close to flat, with any curvature too small to detect. The flatness problem puzzled cosmologists for decades. Why should the universe be so precisely flat? Any deviation from flatness in the early universe would have grown over time, yet we observe near-perfect flatness after 13.8 billion years. This fine-tuning problem, along with the horizon problem of why distant regions have the same temperature, despite being causally disconnected, motivated the development of inflation theory. Cosmic inflation, proposed by Alan Guth in 1980, suggests the universe underwent exponential expansion in its first fraction of a second. This rapid expansion would flatten any initial curvature, solve the horizon problem by expanding a small, causally connected region to encompass the observable universe, and generate quantum fluctuations that seeded structure formation. While inflation elegantly solves several cosmological puzzles, its physical mechanism remains uncertain. Dark matter emerged as another cosmological mystery. Galaxy rotation curves, gravitational lensing, and the cosmic microwave background all indicate that most matter in the universe doesn't emit or absorb light. This dark matter, about 5 times more abundant than ordinary matter, forms the gravitational scaffolding on which galaxies and clusters formed. Despite decades of searches, dark matter's nature remains unknown, though weakly interacting massive particles and primordial black holes are among the candidates. The discovery of cosmic acceleration in 1998 shocked cosmologists. 2 teams studying distant supernovae found that the universe's expansion is accelerating rather than slowing as expected from gravitational attraction. This acceleration requires a repulsive force, dubbed dark energy, that comprises about 68% of the universe's energy density. Dark energy might be Einstein's cosmological constant, representing vacuum energy, or something more exotic like quintessence, a dynamic field that varies with time. The standard model of cosmology, lambda CDM, combines cold dark matter with a cosmological constant to describe the universe's composition and evolution. According to this model, the universe consists of about 68% dark energy, 27% dark matter, and only 5% ordinary matter. This means everything we see, all stars, planets, and atoms, represents less than 5% of the universe's content. The rest remains mysterious. General relativity predicts that gravitational waves from the Big Bang itself might be detectable. These primordial gravitational waves would have left an imprint on the cosmic microwave background's polarization. While not yet definitively detected, their discovery would provide a window into the universe's first moments, potentially revealing physics at energy scales far beyond terrestrial experiments. The universe's ultimate fate depends on dark energy's nature. If dark energy is truly constant, the universe will expand forever, with galaxies eventually disappearing beyond our cosmic horizon. If dark energy strengthens over time, it could lead to a big rip where even atoms are torn apart. If it weakens or reverses, the universe might eventually recollapse in a big crunch. Current observations favour eternal expansion, leading to a cold, empty universe in the far future. Black holes play a crucial role in cosmological evolution. Supermassive black holes at galactic centres influence galaxy formation and evolution through feedback processes. Active galactic nuclei can regulate star formation by heating or expelling gas. The merger of galaxies leads to black hole mergers, producing gravitational waves that LISA and other future detectors will observe. In the far future, black holes might be the last remaining objects, slowly evaporating through Hawking radiation. The multiverse concept emerges naturally from some cosmological theories. Eternal inflation suggests our observable universe is one bubble in an infinite ensemble of universes with potentially different physical properties. String theory's landscape of possible vacua could manifest as different universes with varying constants of nature. While scientifically controversial, the multiverse might explain apparent fine-tuning in our universe's properties. Cosmological observations test general relativity on the largest scales. The growth of structure, gravitational lensing by clusters, and the integrated Sachs-Wolf effect all probe gravity's behaviour across billions of light-years. So far, general relativity successfully describes all observations, though dark matter and dark energy might hint at modifications needed on cosmological scales. Alternative theories like modified Newtonian dynamics attempt to explain observations without dark matter, but face significant challenges. The intersection of quantum mechanics and cosmology raises profound questions. How did the universe begin? What happened at the Big Bang singularity? How did quantum fluctuations during inflation become classical density perturbations? These questions require quantum gravity, as general relativity alone cannot describe the universe's earliest moments when quantum effects dominated. Modern cosmology reveals a universe far stranger than early astronomers imagined. Space itself is expanding, carrying galaxies apart like raisins in rising bread. The universe had a beginning and will have an end. Most of its content is invisible and mysterious. These discoveries, enabled by general relativity, have transformed our cosmic perspective, revealing our place in an evolving universe of incredible scale and complexity. General relativity has evolved from an esoteric theory understood by few to an essential tool in modern technology and astronomy. Its applications range from the GPS in our phones to the detection of gravitational waves from colliding black holes billions of light years away. The theory that seemed purely academic for decades now influences daily life and drives cutting-edge research across multiple fields. The global positioning system represents general relativity's most widespread practical application. GPS satellites orbit Earth at about 20,000 kilometers altitude, moving at roughly 14,000 kilometers per hour. At this altitude and velocity, both special and general relativistic effects significantly impact timekeeping. Special relativity causes satellite clocks to run about 7 microseconds per day, slower due to their velocity. General relativity causes them to run about 45 microseconds per day, faster due to the weaker gravitational field at orbital altitude. The net effect makes satellite clocks run 38 microseconds per day, faster than Earth-based clocks. While this seems tiny, GPS positioning depends on measuring signal travel time with nanosecond precision. Without relativistic corrections, positioning errors would accumulate at about 10 kilometers per day, rendering the system useless for navigation. Every GPS receiver effectively performs relativity calculations millions of times daily, confirming Einstein's theories through practical application. Beyond GPS, precise timekeeping for telecommunications, financial transactions, and scientific research requires accounting for relativistic effects. Optical fiber networks must compensate for gravitational time dilation when synchronizing clocks at different elevations. Even the definition of the second, based on atomic transitions, must account for gravitational redshift when comparing clocks at different locations. The International Atomic Time Standard combines readings from hundreds of atomic clocks worldwide, each corrected for its gravitational potential. Gravitational lensing has become a powerful tool in astronomy and cosmology. Strong lensing by galaxies and clusters creates multiple images or Einstein rings of background objects, allowing astronomers to measure mass distributions, including dark matter. Weak lensing statistically analyzes subtle shape distortions of millions of galaxies to map the dark matter distribution across vast cosmic volumes. Microlensing detects exoplanets and other compact objects by observing temporary brightness increases when they pass in front of background stars. The Sloan Digital Sky Survey and other large-scale surveys use gravitational lensing to map the cosmic web structure. By measuring how dark matter bends light from distant galaxies, astronomers can trace the distribution of both visible and invisible matter across billions of light years. These maps reveal how structure formed and evolved under gravity's influence, testing cosmological models and constraining dark energy's properties. Gravitational wave astronomy, inaugurated by LIGO's first detection in 2015, has opened an entirely new window on the universe. Unlike electromagnetic radiation, gravitational waves pass through matter essentially unimpeded, carrying information from regions opaque to light. They provide the only way to observe black hole mergers and probe the universe's earliest moments after the Big Bang. Each gravitational wave detection tests general relativity in the strong field, high-velocity regime. The waveforms from inspiraling binaries match numerical relativity simulations to extraordinary precision, confirming Einstein's theory where gravity is strongest. Future detectors like LISA will observe supermassive black hole mergers and extreme mass ratio inspirals, testing relativity in even more extreme conditions. Multi-messenger astronomy combines gravitational wave observations with electromagnetic and neutrino detections. The binary neutron-star merger, GW17087, was observed across the electromagnetic spectrum, from gamma rays to radio waves. This event confirmed that gravitational waves travel at light speed, constrained alternative theories of gravity, and revealed how heavy elements, like gold and platinum, form in cosmic collisions. Pulsar timing arrays search for nanohertz gravitational waves from supermassive black hole binaries. By monitoring millisecond pulsars for decades, astronomers can detect the subtle timing variations caused by passing gravitational waves. Recent results suggest a gravitational wave background from many distant sources, though individual sources haven't yet been resolved. This technique complements LIGO and LISA by probing much longer wavelengths. Black hole imaging by the Event Horizon Telescope has provided direct visual confirmation of general relativity's predictions. The glowing ring around M87's black hole shadow matches the size and shape predicted for light orbiting near the event horizon. Future observations with improved resolution will test the no-hair theorem and probe the spacetime geometry near black holes with unprecedented precision. Relativistic astrophysics has become essential for understanding extreme cosmic phenomena. Accretion disks around black holes and neutron stars require general relativistic treatment to model correctly. Jets from active galactic nuclei, accelerated to near light speed, exhibit relativistic beaming and time dilation effects. Gamma-ray bursts, the universe's most energetic explosions, involve ultra-relativistic outflows that can only be understood using special and general relativity. Neutron stars provide natural laboratories for testing general relativity with matter at nuclear densities. These objects, with masses comparable to the Sun compressed into spheres about 20 kilometers across, have surface gravities 200 billion times Earth's. Observations of neutron star masses, radii, and orbital dynamics constrain the equation of state of ultra-dense matter and test general relativity in the strong field regime. Quantum field theory in curved spacetime, combining quantum mechanics with general relativity, predicts novel phenomena. The Unruh effect suggests accelerated observers perceive a thermal bath of particles where inertial observers see vacuum. Hawking radiation from black holes arises from quantum effects near the event horizon. These phenomena, while not yet directly observed, influence our understanding of black hole thermodynamics and the information paradox. Cosmological applications of general relativity continue expanding. Weak lensing surveys map dark matter and dark energy across cosmic time. The integrated Sachs-Wolf effect, where cosmic microwave background photons gain energy traversing growing potential wells, probes dark energy's influence on structure formation. Baryon acoustic oscillations, frozen sound waves from the early universe, serve as standard rulers for measuring cosmic expansion history. Future experiments will test general relativity with unprecedented precision. The square-kilometre array will monitor thousands of pulsars, detecting nanohertz gravitational waves and testing gravity in extreme conditions. 30-metre class telescopes will measure stellar orbits near galactic centre black holes with exquisite precision. Space-based gravitational wave detectors will observe massive black hole mergers across cosmic time. Quantum gravity research increasingly relies on insights from general relativity. The holographic principle, inspired by black hole thermodynamics, suggests gravity might be emergent from quantum entanglement. Loop quantum gravity attempts to quantize spacetime itself, potentially resolving singularities in black holes and the Big Bang. String theory incorporates general relativity as a low-energy limit while predicting modifications at the Planck scale. Alternative theories of gravity, motivated by dark matter and dark energy puzzles, make testable predictions distinguishing them from general relativity. Modified Newtonian dynamics attempts to explain galaxy rotation curves without dark matter. Scalar tensor theories add additional fields to Einstein's theory. Massive gravity theories give the graviton a small mass. Each alternative makes specific predictions that observations can test. The search for violations of the equivalence principle continues with ever-increasing precision. Lunar laser ranging tests whether Earth and Moon fall toward the Sun at the same rate to parts in 10 to the 13th. Satellite experiments like microscope test whether different materials fall at the same rate to parts in 10 to the 15th. Any detected violation would revolutionize physics, indicating new forces or modifications to general relativity. Gravitational physics influences fields beyond astronomy and cosmology. Analog gravity experiments use fluids, Bose-Einstein condensates, and other systems to simulate black holes and test theoretical predictions. The ADS-CFT correspondence connects gravitational theories to quantum field theories without gravity, providing new tools for understanding strongly coupled systems. Gravitational concepts appear in condensed matter physics, from topological phases to emergent geometry. The technological requirements for testing general relativity drive innovation across multiple fields. LIGO required developing the most sensitive measurement devices ever built, advancing laser stabilization, vacuum technology, and vibration isolation. Atomic clocks for testing gravitational redshift achieve fractional frequency stabilities of parts in 10 to the 19th. These technologies find applications in quantum computing, precision measurement, and fundamental physics research. Educational and cultural impacts of general relativity extend far beyond physics. The theory has influenced philosophy, challenging concepts of absolute space and time. Science fiction regularly features black holes, wormholes, and time dilation, bringing relativistic concepts to popular culture. The image of Einstein as the archetypal genius has shaped public perception of science and scientists for over a century. General relativity's success story demonstrates how fundamental research, driven by curiosity about nature's workings, can lead to practical applications decades later. Einstein couldn't have imagined GPS when developing his theory, yet billions now depend on relativistic corrections for navigation. This pattern repeats throughout science history, reminding us that today's esoteric theory might be tomorrow's essential technology. The theory's mathematical beauty continues attracting physicists and mathematicians. The way physical phenomena emerge from geometric principles suggests deep truths about nature's structure. General relativity's success in describing gravity geometrically has inspired attempts to geometrize other forces and find unified theories. Whether all physics can be understood geometrically remains an open question driving current research. Modern computational capabilities have transformed general relativity research. Numerical relativity simulations model black hole mergers, neutron-star collisions, and cosmological evolution with extraordinary detail. These simulations, requiring supercomputers solving Einstein's equations on adaptive meshes, predict gravitational waveforms and electromagnetic signatures for comparison with observations. Machine learning techniques increasingly aid in analyzing complex datasets and identifying signals in noisy data. International collaborations have become essential for major relativity experiments. LIGO and Virgo involve thousands of scientists across dozens of countries. The Event Horizon Telescope links radio telescopes worldwide to create an Earth-sized interferometer. These collaborations demonstrate how modern science transcends national boundaries, uniting humanity in the quest to understand the universe. The theory of relativity has profoundly influenced not just physics, but our entire worldview, challenging fundamental assumptions about the nature of reality, causality, and our place in the universe. These philosophical implications extend far beyond academic philosophy departments, shaping how we think about time, existence, and the relationship between observer and observed. As we near the end of our journey through Einstein's revolutionary ideas, it's worth reflecting on what relativity means for our understanding of existence itself. The relativity of simultaneity strikes at one of our most basic intuitions about time. We naturally think of now as a universal moment, extending throughout space, dividing the fixed past from the open future. But relativity shows that observers in relative motion disagree about which events are simultaneous. Your now might include events in my future or past. This suggests that past, present, and future might all exist eternally in four-dimensional space-time, a view known as eternalism or the block universe. In the block universe picture, time doesn't flow or pass. Instead, all moments exist timelessly, like frames in an eternal film reel. We experience the illusion of temporal flow because our consciousness is somehow confined to experiencing these moments sequentially. This view challenges free will, suggesting the future already exists as definitely as the past. Yet it also offers a kind of consolation, implying that all moments, including those we've lost, exist forever in space-time's eternal structure. Not all physicists and philosophers accept eternalism. Some argue for presentism, where only the present moment exists, though this is hard to reconcile with relativity. Others propose growing block universes, where past and present exist, but the future doesn't yet. The debate continues, with relativity providing constraints, but not definitive answers about time's ultimate nature. The equivalence principle reveals deep connections between gravity, acceleration, and the structure of space-time. The fact that all objects fall at the same rate regardless of composition, which seemed coincidental in Newtonian physics, becomes necessary in general relativity. Gravity isn't a force, but the curvature of space-time itself. This suggests that what we perceive as forces might be manifestations of geometry, hinting at a fundamentally geometric nature of reality. The speed of light as an absolute limit has profound implications for causality and information. Nothing can travel faster than light, not because of some cosmic speed limit sign, but because the structure of space-time itself prevents it. This protects causality, ensuring that causes precede effects in all reference frames. It also means that vast regions of the universe are forever beyond our reach, establishing absolute horizons to both knowledge and influence. Black holes embody the extreme consequences of general relativity, regions where space-time curvature becomes so intense that classical concepts break down. The information paradox, arising from Hawking radiation, forces us to confront fundamental questions about information, entropy, and the nature of physical law. If information can be destroyed in black holes, it would violate quantum mechanics' unitary evolution. If it can't, we must explain how it escapes, potentially requiring radical revisions to our understanding of space-time. The holographic principle, inspired by black hole thermodynamics, suggests that all information in a volume can be encoded on its boundary. This implies that our three-dimensional world might be a projection of information stored on a distant, two-dimensional surface. If true, this would fundamentally alter our understanding of space, suggesting that the dimensions we experience might be emergent rather than fundamental. Cosmological implications of general relativity raise questions about existence itself. The Big Bang singularity, where classical general relativity breaks down, marks not just the beginning of matter and energy, but of space and time themselves. Asking what came before the Big Bang might be meaningless if time itself began then. This challenges our ability to reason about ultimate origins using concepts derived from within space-time. The discovery of cosmic acceleration and dark energy suggests that empty space has properties, an energy density that drives expansion. This vacuum energy raises questions about nothingness itself. Is truly empty space possible, or does the quantum vacuum with its virtual particles and vacuum energy represent the closest approach to nothingness? The cosmological constant problem, the vast discrepancy between observed and calculated vacuum energy, remains one of physics' greatest puzzles. The multiverse concept, arising from inflation and string theory, challenges the uniqueness of our universe. If countless universes exist with different physical laws and constants, it changes how we think about fine-tuning and existence. The anthropic principle, suggesting we observe conditions compatible with our existence simply because we couldn't observe otherwise, becomes more plausible in a multiverse context. But it also raises questions about the scientific status of theories predicting unobservable universes. Relativity's impact on philosophy extends beyond metaphysics to epistemology, the theory of knowledge. The theory emerged not from new experimental data, but from Einstein's analysis of fundamental principles and thought experiments. This demonstrates the power of pure thought in discovering nature's truths, validating rationalist approaches to knowledge. Yet the theory's confirmation through observation validates empiricism. Relativity thus supports a synthesis where theoretical reasoning and experimental verification work together. The role of mathematics in relativity raises questions about the relationship between mathematics and physical reality. Why does the universe obey mathematical laws? Is mathematics discovered, existing independently of human minds, or invented, a creation of human thought that happens to describe nature? General relativity's geometric formulation suggests that geometry might be more fundamental than matter, that the universe might be essentially mathematical. The observer dependence of measurements in relativity has been misinterpreted to support relativism in other domains. Some have incorrectly claimed that relativity shows all viewpoints are equally valid, or that objective truth doesn't exist. In fact, relativity establishes new absolutes: the space-time interval, the speed of light, and the laws of physics themselves. It shows that while observations are frame-dependent, there's an objective reality described by invariant quantities. Relativity has influenced fields far from physics. In literature and art, it has inspired explorations of time, perspective, and reality's nature. The idea that time passes differently for different observers has become a metaphor for subjective experience. Science fiction has extensively explored relativistic effects, from time dilation enabling travel to the future to the paradoxes of faster-than-light travel. The cultural impact of Einstein himself has been enormous. His image has become synonymous with genius, his equations symbols of incomprehensible complexity. This has both positive and negative effects, inspiring interest in science while also reinforcing stereotypes about who can do physics. Einstein's own views on politics, religion, and philosophy have been endlessly analysed and often misrepresented. Looking forward, general relativity remains central to many of physics' deepest questions. The quest for quantum gravity seeks to reconcile general relativity with quantum mechanics, potentially revealing spacetime's quantum structure. Dark matter and dark energy might require modifications to Einstein's theory or reveal new physics beyond it. Gravitational wave astronomy has just begun, promising discoveries we can't yet imagine. The theory's technological applications continue expanding. Future space missions might use relativistic effects for navigation and communication. Quantum technologies might exploit the interface between quantum mechanics and gravity. As we venture further into space, relativistic effects will become increasingly important for mission planning and execution.